we are right now. So we defined notions of fairness. We talked about different ways in which you could build algorithms to achieve fairness in learning. And we yesterday spent a lot of time talking about one particular technique for achieving fairness in learning, namely how to modify your input data so that when you train an oblivious classifier on the data, you will get fair outcomes. And of course, we had a lot of argument about whether it's reasonable to change the data and under what conditions it might be okay to mess with the data, under what conditions it may not be okay. And these are all discussions we had. And the central idea there was to somehow remove the information in the data that might be used later on by a classifier. And depending on what you knew about the classifier, either you could be more specific about removing information, or you could say, like we talked about yesterday, assume nothing about the classifier and try to use information theoretic arguments to pull the data, to pull the information out. Okay? And so this whole class of approaches is one way to deal with the problem of bias in your analysis in a way that allows you to not have to pay attention to what classification scheme you're using, at least in principle. But the methods we're going to study today are more specific. They're more methods that work when you are the person who wants to build the fair classifier and you care about building something reasonable. So you have a lot more control over what you're doing, right? You can bake a whole lot of things into the classification process itself. So you don't have to worry about the data. You can pretty much, you might decide to modify the data or you might not. But the point is you're working inside the model right now. And so what that means is that the techniques we're going to look at tend to vary a little bit. They vary based on what kind of model they're building. If you're building a decision tree, it might look like something. If you're building an SVM, it might look like something else. So there isn't the same kind of overall common set of tools that we're going to be using. But the ideas are similar in many ways. Right? And so that's what we're going to talk about today for the first session and for the second session as well. Okay? All right. So if you, again, go back to the history. So I first have a question. So how many of you read any of the papers for today's reading? 1, 2, 3. Aha. See, I had mentioned this is one thing I wanted you to do, to go read the papers. If you had some extra time yesterday, do that. So it actually helps to read them, even if you don't fully understand what's going on, because you get some ideas about what's happening. And then when I talk about it in class, you can put the whole thing together. But if you come in completely cold, it's going to be a little bit harder to follow some of the technical details of what's going on. So keep that in mind for next couple lectures. So what we're going to talk about today is one of the first papers that attempts to build a classifier that does a reasonable thing with regard to fairness. Right? And again, in all of these systems, the basic rule of thumb is you first have to, so remember, we're doing fairness-aware modeling. Right? So this is distinguished from the previous setting where we were just modifying the data so we could do whatever we want. Here we're explicitly baking fairness into the model, which means we have to do a couple of things. We first have to decide what model, and then we have to decide what fairness, what measure of non-discrimination or fairness are we using. Right? And so again, based on what answers we give to these questions, you'll end up with different methods. Right? And I think because of the relative newness of this area, what we don't have yet is a clear synthesis that says, look, for this class of models and for this class of functions, this technique is the one you want to use. We don't quite have that yet. We're still kind of, so necessarily the methods I'm going to be describing are going to be much more, I would say, low level in the sense that they are at the level of what you might see in a paper, but they're not the level of what you might see in a textbook or something. So we're still working those details out. Okay? Some of this on the first day. So would someone like to tell me what a decision tree model is? Any volunteers? Anyone? You spent that whole first day learning what decision trees, right? Because you covered some. So prove that you actually remember the stuff that he told you. Anyone want to start? So, pretend you're giving her the lecture on decision trees. What do you start with? That's okay. But even what is a decision tree? Okay, so let me rephrase the question. What is a decision tree? And I know you were playing with this in the lab the other day, so it's not like you haven't seen them. You've literally seen a tree.
At each point of label, you get multiple choices and you pick out the best.
So can you be more specific? So I have a tree. Okay, so I have a node in a tree, and what happens to this node?
Root node. This is a root node.
There's a root node, okay?
Which is having maximum information in order to classify any data as per the.
Sure. So what? So I go to the root node. What happens next?
It has various
Attributes. So the data has attributes. So the data has attributes, let's say A1 through AK. Okay, now what? Okay. That's fine. You want to choose the best attribute, but what? So I've chosen it. Now what? What do I do there?
You have to find out the rules.
Right. So what is the what? So how do you express the rule? So there's some kind of statement here, right? So it's basically there's a question here. You know, AI is equal to something, right? And based on the answer to that question, you might get different paths, right? Okay, so now what happens here? Let's say you come here. What happens next? It might be a different attribute, right? So it might be, you know, AJ equal to something, and you go here. Okay, so we keep going for a while, and we end up at a leaf, right? What do we expect at the leaf? What happens at the leaf? Sorry, someone in new. Yes, go ahead. So at this point, you've come out. You took your input. You come all the way down here. So what now?
Then it will be a class label with the properties associated with it.
So there'll be a class label here, right? And so basically, every time you want to classify a new item, which is what the classifier is supposed to do, you run it through this. Oh, here's the answer, right? And the model is this whole thing, right? So the process of learning is the process of building this thing, right? Because once you build it, it classifies your things for you. It's a very simple model. It's very easy to understand. And it's also, you know, and that's one of the reasons why it's a very popular model. And that's it. So now the question is, okay, well, a couple of questions. First of all, how do we build such a thing? And secondly, how do we build it in a way that might capture sort of principles of fairness that we've been studying? Okay? Okay, good. So before we go here, let's think a little bit about how we build decision trees. And there are many ways to build decision trees, different variations based on how you decide to expand out a node. But there are basically a couple of choices here. The main choice is, okay, at this point, what question do I want to ask, right? What question do I want to ask? And then once I ask the question, there are a bunch of answers. Then again, I decide, okay, what question do I want to ask now? Okay, what question do I want to ask now? You're playing 20 questions essentially, right? Someone's guessed a number in their head and you're asking them a question and trying to figure out what to do. And of course, the goal in all of this is to make a tree that is, you know, not too deep. You want to answer your question quickly, but you want it to be kind of useful, getting good answers here.
Why do you want that? The tree should be a shallow.
Well, one reason that the tree might be nice for the tree to be shallow is that the time it takes you to answer any question is the depth of your tree, right? So if you have to answer more questions to get a classification for a point, this point comes along and say, hey, classify me, and you're like, it'll go on forever before you get an answer. So while it's not mandatory that you must make it as short as possible, it's a desirable property, right? Okay. And that desirable property to make your tree shallow basically defines the main strategy or meta strategy for building a decision tree. And all of you have been hearing mentions of this strategy already in the discussion we just had, this idea of information gain, right? Okay. So the way to think about information gain in a decision tree is to forget about decision trees. Think about something you've all learned about, binary search. You've all heard of binary search, right? So you all know that. You all have played 20 questions. If I guess a number, think of a number between 1 and 10,024. Within 10 guesses, you should all be able to figure out what I've got, right? How do you do that? Well, in binary search, we just say, okay, look, we have some range. The number could be anywhere here. And we ask a question, and then the answer tells us to go left or right, and we keep going. And of course, everyone knows the strategy for doing this, right? So what's the strategy? What do you do? What do you do? Best way to get the answer?
Choose the middle.
Choose the middle, right? And then what do you do?
And then
It'll tell you left or right.
whether the number is
Yeah? Suppose it says go this way, again choose the middle. Why do you choose the middle?
just so that we can divide it into two halves.
Why do you want two halves?
So that time complexity becomes log n.
Why?
Log n is the least value.
But why? Why does it become log n?
To get the fastest.
No, no, no. That's why you want log n. But let me see if I can rephrase the question. Why does asking it in the middle get you that?
Because it balances out those two halves.
It balances sides. It's essentially it is the one that on average gives you the most information about what's going to happen next. Because if you were to ask on one side, you might get lucky in the answers here, or you might get unlucky in the answers here. Conversely for this way you kind of balance out the effects of the two sides to maximize the amount of information you've got from your answer, right? So this idea of asking a question that is maximally informative is at the heart of binary search, although we never phrase it in such a complicated way. But when you think about it that way, that's exactly what you're doing in decision trees. A decision tree is just a glorified binary search, right? You're just building a binary search tree. And so this idea of maximum information gain, though, in a decision tree is a little bit more complicated than it is for a binary search tree. In a binary search tree, it's very simple. In the middle, there's equal numbers of things on both sides, you're happy. But what does information gain even mean for a decision tree? Right? What does that even, how do you define such a thing? What is the goal here? The goal in a decision tree is to get to a leaf as quickly as possible which has a single label. Right? It's not getting to any leaf, right? That's not the point here. The point is to be able to clump your items or clump your labels into categories so that anything that goes along the path gets that label, and that's going to be the correct answer for that. Right? So you don't have to, so you get these single answers there. So in other words, what are desirable questions in a decision tree are questions that lead to answers where there's only one answer, essentially. Right? So there's only one way to answer the question. So if you were to, let's say you had a data set, right? And it turned out that if you take a particular attribute, let's say this is attribute A, and if it was 5, your classification value was 0, and if it was 6, the classification value is 1. And it was perfect. This is a perfect split. Then what your system should tell you if you build a proper decision tree is that don't waste time asking questions about any of the other attributes. If you ask about A, as soon as you ask about A, you get a big 0 here, and you get a big 1 here, and you're done. Right? You've got maximum information about what's going on. Right? Okay. So keep that in mind. So how do you quantify this, right? So what you're trying to say is that, what you want to say is, how much information am I going to gain by by asking this question based on where I was before? Okay? And one way to quantify that is to think about, again, going back to information theory, the idea of entropy. Okay? So let's see what that means. So let's define the entropy of the class entropy of a data set. So we have a data set D. Sorry, making noises at me. Okay. So how many of you are familiar with entropy in general? Not too many. Okay, so maybe I should define entropy first before I define this fancy class entropy. Okay. So what is the entropy of so entropy is a function of a probability distribution, right? So I have some probability distribution, which means I have probabilities, think of it in the simplest case, I have, n objects, and each of them has a probability. right? So if you think of, let's say, a six-sided die, right? If you have a good dice, then each side has probability 1 over 6 of appearing. This is a distribution, right? Okay, once I have a distribution, I can define entropy. So the entropy of a distribution, technically the entropy of a random variable, but it's just a formula. It's basically, okay. So there's nothing special about this. I mean, just as I've written it, just a formula. But it turns out that the entropy is a very, of course, powerful notion. It in some sense captures the minimum amount of information needed to describe this distribution on average. In other words, if you had a distribution with this much entropy and you want to write down an element, so you took a sample, you want to write it down, the number of bits you would need to write it down would be this much. Okay? For example, if you have n objects, each of them is equally likely. If you compute this, you'll get log n. So the h of 1 over n is equal to log n. This is base 2, but whichever base you want. And that says, oh, you need log n bits to write down a sample from a distribution of n elements, which is like saying if you have n objects and you want to describe them, you need log n bits. This we all know, right? But this is a way of saying that there's an entropy function here. Now, why the entropy is different from log n? Because if some elements are more frequent than other elements, then you can be more clever in the way you encode them. You could sort of use fewer bits for more frequent elements, use more bits for more rare elements. On average, you'll end up with a net gain in the number of bits you need. And this is what is called Huffman coding, and there's a whole other beautiful thing that I will not discuss here. But at any rate, if you think of entropy as capturing the amount of information content in a system, which is a very useful way to think about entropy in this context, then this seems to have the thing we need. We're talking about information gain. How do we measure information gain? Oh, we can use entropy to measure information gain, right? See the amount of information in the system here, see the amount of information in the system here, and see the difference between them. But you can take this idea all the way to the end. At the end, if you ask yourself, okay, how much information is in the system here? Well, this is a probability distribution. It has basically the probability of if you think of the class labels, the probability of the class label being 1 is, well, 1. The probability of the class label being 0 is 0. If you plug that into your calculation, the entropy is 0. There is no information left. Why? Because you know the answer. There's nothing there. So it seems like the goal here is to get to a point where there's no information left, right? So it's like you have a budget. In the beginning, you have lots and lots of information. You take one step, information reduces. You take another step, information reduces. You want to keep reducing information as much as possible so that at the end, there's nothing left, right? Okay. So how do we measure that? The key here is that we're not looking at information in general. We're only looking at information with respect to the class label. That's the only information we care about. Can we tell what the class label is or not? And so what we're going to define is a kind of is a certain kind of entropy, the class entropy. Okay, which I'll define as follows. Look at the data set and look at how many. So let's say Ni is equal to the number of items in D from class I. Okay. So maybe we have a 4-class labeling of the data. That's what you want to do. One of the good things about decision trees is that they're not limited to binary classification. You can do multi-class classification very easily with them, right? And so you have Ni items in class I, and so you can write down a probability, which I'll say within quotes because it's not a probability so much as just a fraction of items. Ni over D, the size of the data set, is equal to Pi. Okay? Well, now I have Pi's, I can compute an entropy, right? So now the class entropy as we said before. So for example, if you have a data set where you have only one class, what is the entropy of that data set? The class entropy of the data set? You have only one class. So we have basically P1 is equal to 1. What is the entropy of such a system? 0. No information. Okay. Suppose you have a set that's sort of evenly balanced between two classes. what will the entropy of the system be? 1 log 2, right? So it'll be half log 1 over half plus half log 1 over half, which is equal to log 1 over half, which is equal to 1. Log 2 is 1, right? So this is one bit of information. So similarly, if you have a data set with, you could have different numbers of items in each class, you'll have some amount of class entropy, right? Okay, so that's the starting entropy at the root. That's all the information we have right now about the classes. And remember, we want to get down to a place where the class entropy is 0, right? So what we want to do is choose a question to ask so that we make as much progress as possible in going to 0, right? So in other words, how do we talk about this? So here's how we say this. So what we say is that let's say we make a decision. So we ask some question and we get some answer, right? And because we've asked a question, is my attribute value blah, 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 some items from the data would be in this category, some would be in that category, and some would be in that category, right? So if you think of your data set D here, you effectively, by asking this question, have split your data set into D1 up to D, I don't know, K, whatever the values are. Right? So you had some entropy before, you have some entropy now. Right? How much entropy do you have here? Well, you can write down the class entropies for each of these data sets. That's fine. But you have to combine them. And intuitively, how would you combine them? Well, if one data set is much more than bigger than another one, its class entropy carries more weight. Right? So you can write down this as, so the class entropy of this, right? This entity here is going to be sigma I equal to 1 to k. The fraction of items in that set, right, which is the weight for its own class entropy. Right? And actually you can work this out. You can sort of verify that this will actually be the correct way to express this. Because you first make a choice to come down here, and then you take that entropy. So that's the weighted entropy of the system here. And it's not hard to see because entropy is a concave function that this number will always be less than that number. It'll never be more. And this is intuitively nice because it means by asking a question, you shouldn't be able to add information to the system. Right? That doesn't make any sense. And the mathematics works out correctly. That in fact you will reduce the amount of information. But now you have an easy problem because now you're saying, okay, I started off with this, I ended up with this, so now I can quantify the gain in information, the amount I have learned about my data by asking this question as this is called the information gain. And again, there are many variations on decision trees. Not all of them use entropy, but they all use some notion of information gain, right? So the information gain here is basically saying, I started off with this much that's, sort of uncertain or unknown in my data. I've asked this question, I've now collapsed to this, right? So you can think of entropy as the amount of information and also the amount of uncertainty in the data. The less entropy, the more certainty you have. When the entropy is 0, you are sure. So when we think about this as I'm uncertain here up to this level, I'm uncertain here up to this level, the difference between them is the amount of uncertainty I've reduced. And so the goal in decision tree building then is to be greedy. Is to say at every step, let me choose a question to ask to maximize this quantity. And that's how you build decision trees. Okay? And there are strategies to, you could imagine, there are sort of brute force strategies you could imagine using where you say, okay, take an attribute, look at the split for that attribute. For each attribute, what you can do is you can say, okay, for this attribute, look at how the data set would split for different values of this attribute, and do this for each attribute in my data set, and then pick the one that's the best, do it, and then repeat. It's actually not that hard to do. And there are maybe smarter algorithms in this as well. But if you didn't know anything else, you could at least do that. You could just say, okay, let's go over for each attribute, compute this quantity, and then do this over again. Yeah?
How do you know the locally optimal strategy is also globally optimal?
You don't. You don't. There's no guarantee that you can get something that's globally. And first of all, what is globally optimal?
As in, like, we are asking questions and just give more information.
No. Well, what is globally optimal?
As in, like,
what is the definition of optimal?
which gives, like in this case, a decision tree which will give us the most information gain.
No. But what does that mean? Every decision tree gives you as much information gain as there is information in the data set.
Okay, so like compared to the decision tree which can give us the maximum, like they can.
You're not defining optimality still. You're sort of
One MMB best applicable.
But what's best?
The least depth.
Okay, so you might not agree, but at least that's a concrete measure with the least depth. So does this procedure give you the decision tree of least depth? I don't think so. I doubt that very much. But at least you can ask that question. You can say, can I? But you might argue, I don't care necessarily for the one of least depth. It's a nice feature to have, but I don't care that much. Maybe a deeper decision tree has more information in it about what decisions are being made. And that might be okay too. Which is why for decision trees, this idea of, okay, let's define an optimal decision tree and try to optimize it is not necessarily the right strategy. It depends on what you want to do with your tree. If your goal is speed, that you're building a classifier that's going to sit on your phone and has to be very, very quick at answering, sort of doing classification, then maybe the least depth tree is a good thing to have. Or maybe not. Right? So it really depends on the problem, what best is, which is why I'm not talking about best right here. See, if this was a class I'm teaching next semester in algorithms, I'd be ranting and raving about how we must define optimality and we must prove things are optimal. But this is not that class, so I'm not going to do that. So, but that's fine.
What should be the strategy for pruning the tree?
Pardon me? Pruning. What do you mean? What do you mean pruning the tree?
Pruning, like if we are getting more depth, so
yeah.
we can reduce the depth.
That's a good question. Not being an expert in decision trees, I'm not sure I can tell you that. My feeling is that if you have too much depth, somewhere along the way you made some local choice that has now split your data into sets which are problematic. So like any greedy strategy, if the greedy strategy is actually leading to a bad outcome, you've made some local decisions that are bad, and you might want to go back, maybe move back up the tree and change some of your decisions around to see it. I'm not actually sure how you do that.
But there are correlations, partially we take random choices and we build a random forest. So actually a random forest is now as
yes.
also remarked, and it gives better results in those cases. Otherwise, the decision tree is able to take away or sort of delete the irrelevant features by itself. That's one property, and hence, if you go for a greedy approach and have maximum reduction in uncertainty or maximum information gain per step, then you get greedy.
So in other words, in most cases it works well. In the few cases where it doesn't work well, doing something at random and trying to be, so that's a very good point, right? So I mean, and this is a very good intuition for about why random forests are helpful. If in fact our greedy strategy of trying to do the best at every step is tripping us up, then let's not try to do the best, let's just be clueless and be random. And then do this a number of times, you get a random forest, and they are also very useful. So I like that intuition. So it helps think about what you do in those cases, yeah. Okay? Right. And it's also, and another good thing about a decision tree is that you can see what it's doing. And we'll talk about this, so there's a whole section we're going to talk about in interpretability and how that's an important aspect of this larger issue, that you can't talk about fairness if you can't really see what your method is doing. And with a neural network, you don't know what it's doing, but with the decision tree, you can see every single step of the way how it's making its decision. And if someone says, oh, let me look at the color of your shirt today, and it's like, why are you looking at the color of my shirt? And then you can go back and, okay, maybe the model has got a problem, we got to go look at it. You can't do that with other methods. So there are many good things to say about decision trees, and that's why they're a good platform to start thinking about this problem. Okay? Okay, good. So as I said, this is basically the way you can build a decision tree. Define some notion of information gain, and again, entropy is the natural one to use, but I'm not saying that's the only one. You could imagine other methods. We've seen decision tree examples in the lab where we're using the Gini index and things like that to sort of build these things, and that's fine. So once you have a decision tree now, you're done. And so now we can actually talk about the problem of how to instrument them to be less biased. Okay? But before I do that, are there any questions about decision trees? No? It's all good? Okay. So the idea of how to use decision trees in the context of fairness is to say the following. That what you're doing with the decision tree is trying to quickly come up with a good answer to your classification task. So you have your data and you want to get an answer where the labeling is all correct. In the process, you're splitting your data. And so what you would be unhappy about is if essentially you had a decision tree that looked like this. This would make you very unhappy as a decision tree builder if you were worried about bias. Because this is a clear case where you're giving a yes answer based on an attribute that you didn't want to have be influenced by this. And of course, if your decision tree has exact questions like this, that's fine. But you could also have questions about, for example, I mean, I'm not asking about your gender, but it kind of correlates with that, right? Or sort of, anyway, at least. Or do you have, maybe not a beard, but. So I'm deliberately being very silly here, right? But the point is that, of course, this issue of correlated attributes makes just inspecting a decision tree to remove biased outcomes a problem. And so the way to think about this problem is to say, in fact, that you have, in some sense, the reverse of what you're doing with the decision tree. In the sense of, what you want to do is be very informative with respect to your class label, but be very uninformative with respect to this other attribute. Let that sort of sink in for a minute. So what I'm trying to say is that as you go down the decision tree, you are also learning something about your data. Right? Your data is becoming more specifically profiled. It's going to have more specific information about the attributes because you're pruning things out. If it turns out that in the course of doing the pruning, you had narrowed down your sensitive attribute information to one corner, then you have gained a lot of information about it. Right? So if you ask some questions, so now we have a much more general decision tree, and you're going down and you're asking questions, right? And let's say you've got a while to go, but at some point you've discovered that basically everyone here is male, everyone here is female, everyone here is female, and everyone here is male. You've essentially segregated your population, at least gender-based, into groups like this, right? And if you now if you think of this notion of entropy, if you say, well, what is the entropy with respect to my attribute, not with respect to my class label? That entropy is now very small, because all of these entropies are zero, because you've really honed in on that. And this is the argument is that this is now a problem, because now you're going to make separate decisions for different groups, and this is prone to be biased. And so some of the solution to this problem is to build a tree in which, while still doing your class label investigation, you try to keep these groups as confused as possible. So if you went down all this way, and at this point you still have a pretty good mix of male-female, then you're confident that your process is not separating out the groups in any way. So you want to ask questions to maximize your information gain with respect to the class. But you also want to ask questions to minimize your information gain with respect to the sensitive attribute at the same time. This is the idea of this paper. That you want to balance out these two concerns. So what does this mean? Just like we defined the class entropy, we can define the attribute entropy. Namely, Ni is equal to the number of items in B from attribute value, whatever. So M is the number of male and F is the number of female, and you can write down the entropy for that group. Once you have the entropy, you can define the information gain, exactly the way as before. You have the entropy with respect to the attribute at the top, you have the entropy with respect to the attribute at each of the children, and you compute this quantity. So just like we defined information gain with respect to class labels, you can define information gain with respect to your attributes. And now it's a question of balancing them out. Okay? So having said that, what would you do? How would you build your decision tree now? I've given you enough information now to describe a basic procedure. What do you do? So I start off with a root node. What's next? How do I decide how to split? What question? How do I decide what question goes in there? Yep.
We can write objective functions so that information we will choose a parameter some way and some information gain. The objective function will be information gain minus information gain attribute information gain. So we need to maximize that. So
Okay, good. So the statement here says something like this. Yeah, so what we want to do is, we know that we want to maximize that quantity, right? So we want to, at every step, our goal has been so far to maximize I class, let's say. But now we have this other thing that we want to keep very small. We want to minimize the gain there. And so a typical way to do this would be to say something like, right? With this is some tuning parameter. Because if you maximize this quantity, you're trying to make this high, and you're trying to make that small. And in fact, this is one of the methods. So this paper proposes 3 different methods for trying to do this, and this is one of the methods they propose. They actually put lambda equal to 1, but that's fine. Another plausible way you could do this, and again, these are just useful tricks to keep in mind. They're not, I don't think they're very important, but you can always do something like this. It has the same effect, but it's scaled differently. This has the, again, depending on what you prefer, you might choose one versus the other. But there's no real difference, really. In some sense, they're both trying to capture the same idea. Okay? And so these are 2 of the methods that they propose in this paper to try and build these trees. So the paper tries something else, which is extremely strange. Can you see why this is very strange? Can someone tell me why this is strange?
Because you are maximizing the attribute and you want to minimize it.
Yes, exactly. It's the exact opposite of what I've been insisting we should do so far. What I find very interesting, and what the authors argue, but we can, again, they argue this, but we can discuss this, is that what both of these methods are trying to do is eliminate any knowledge, essentially minimize any knowledge you might retain about the attribute as you go down. Right? as far as possible. Whereas this is saying, no, let's keep as much information as possible. Now this, of course, is going to work terribly from the point of view of maintaining unbiased decision making. But what they do is they combine this with an output modification technique. And we talked about this very briefly early on. We said there were 3 ways to build fairness-aware systems. You modify the input, you modify the classifier, and modify the output. This is doing the second 2 things. It's going to build a classifier, but it's going to modify the output. And I'll explain what it's going to do in a second. The weird and somewhat non-intuitive thing is that in experimental work, they show that this works better than these. So in some sense, keeping the information around and using it, and then changing your mind at the end, is more effective than closing your eyes and trying to be fair from the very beginning. There is other sort of threads of evidence in the field suggesting that there is reason to believe this makes more sense. That in some sense, it's better to keep the discriminatory information around and then do something at the end, rather than trying to shut it down early on. In some sense, it gives you a better balance of accuracy and quality. But this is a sort of still something we're not quite sure about. But I'm beginning to see in papers little bits of evidence of this kind. So in my mind, this is an interesting observation. That when I first read this paper a couple of years ago, I would not have thought, I would be like, what's going on here? But now I'm beginning to see some signs that there may be something interesting here. Okay. At any rate, so they do, as you can see, once you have such a notion, it's very easy to build a decision tree. And you can do all these things. All I have remains to tell you is, what does this mean here? Right? Because otherwise this is nonsense. So the trick here is the following. So if I'm going to modify the outputs, where do you get the output of a decision tree from? Where do you finally get your answer? At the leaves, right? So you go all the way down to the bottom and you get the leaves. And the leaves tell you the answer. So if you're going to modify the output, the thing you have to modify are the leaves. Right? So imagine that I built my decision tree. I actually use this. So my output is very informative, probably, with respect to both my class label and my sensitive attribute. So I have a bunch of leaves here. The relabeling strategy says, take the leaves, compute the, so here's what the strategy looks like. Okay. So remember, the goal is to get an unbiased outcome as measured by statistical discrepancy. So what do you think we should do? So we've built our tree. We use some measure, maybe one of these things, I don't know which one. And then we've got these things at the bottom. I said that my goal is to somehow relabel them. Change the labels here. How should I do that? Just flip them. Yeah, and see what happens. Let's first do something, let's do a sanity check first, before we try your idea. Let's first figure out, okay, how much bias is there already? Right? So you can actually now compute the statistical bias of this model by running data through it and saying, okay, what's the skew? Right? So we know that the statistical discrepancy says that the probability of the positive outcome, let's say C is equal to 1.
You just find out the information gain with respect to that particular activity.
In the leaf?
For a particular, all attributes. So you know which one is really, is the sensitive attribute really helping in.
Can you make it more concrete for me? So I want to relabel the leaf.
Total information gain with respect to a particular attribute, the sensitive attribute.
Yeah.
Is the information gain is large.
Yeah.
That means we are being biased.
You're being biased, right? And in fact, if you wanted to, that's a good insight there, right? That you can just look at the amount of information gained with respect to that attribute, and the more you have, the more biased it is in some sense. But you can also evaluate it with respect to a model independent measure, just like statistical discrepancy. You can say, okay, what is the probability of seeing this outcome, given that I have this attribute, versus the probability of seeing this outcome, given that I have the other value of the attribute, right? No. This is model independent. What you propose is very model dependent. Like the measure you described would not work for an SVM. But it's a good measure though. But it's a good measure that works for decision trees in specific. Yeah.
Yeah, but I believe this translates to that particular model.
That may be, in some way it might. Probabilities, entropies, kind of, yeah. So I'm willing to believe that there is some way to relate this to that. And that would be actually interesting to look at. Yeah, that's good observation there. So let's first check what the discrepancy is of our system. Maybe it's fine. Okay, so we checked it. It's not fine, right? So it's got some number. So let's say discrepancy is some delta, and it's more than your threshold. This is my threshold, my knob that I want to maintain. Right? I want to maintain only this much discrepancy, and I've got too much right now. So I want to relabel leaves. So now what you can do is you can say, okay, let me take this leaf. So I have some leaf here, and it's got some label. And I want to change it to some new label. Two things are going to happen when I do this. Number one, it will change the discrepancy calculation. Maybe good, maybe bad, I don't know. But it will do one more thing. What will it do? Yes, but something else will go maybe wrong. Pardon me? The accuracy might go down, right? So when you change the label, the bias will change in some way that is unclear, and the accuracy will change, again, in some way that remains unclear. Right? So you can look at the delta, the change in accuracy for a particular leaf if I relabel it to something else. And maybe if there are multiple values, you check for all of them. Right? And there'll be, and more likely than not, the accuracy will decrease as a consequence of doing this. If I built my decision tree correctly, then doing this should only decrease my accuracy. We'll write that down. And so for each leaf, you can do this. For each leaf, you will also have a change in bias caused by that leaf. Right? And you can figure out what that is. So now for each leaf, you write down two numbers. You have a right? My goal now is to relabel some of the leaves. Not all, but some of them. I don't want to relabel all of them. If I can relabel as few of them as possible, I'm happy, right? So I want to relabel some of the leaves with the following property. So my goal now is to choose some subset of leaves, okay, with the following property, that the sum for L belonging to S delta bias, right? So the change in bias achieved, so let's assume this is a positive change, so the bias reduces, is going to be greater than or equal to this. So in other words, you've chosen as many leaves as possible so that this number changes, right? And you want to choose the and then you can write down the accuracy, the change that you get. This is a decrease in accuracy maybe. We'll check the signs to do it the right way. So in other words, the strategy they propose along with this is to say, build your tree first, keep some knowledge about your sensitive attribute. In fact, keep it a lot of knowledge about it. And now when you get your leaves, write down these two numbers for each leaf, which you can compute separately. And then choose some set that balances these two things. And if you stare at this long enough, you will recognize this problem. If you change these things around and make them just arbitrary weights and costs and all, this will look familiar to you. Does it look familiar to you? So let me rewrite this another way. With a bit of sign flipping, it's easy to change this around so it looks like this instead. Why are we doing this? We're trying to change our decision tree after building it in order to balance our desire to be fair. Remember, the whole goal of this.
See, the depth of the decision tree is
Yeah.
very infinity. So in this case, would necessarily be more than or equal to the size of the decision tree, taking only the information base with respect to the class. Because we are summing two things, I class.
Yeah.
So if one of them is lost, the other one will be there.
Okay.
So I class becomes, there's no gain, I attribute my half and gain, or I attribute those no gain, then I. So obviously the size of the depth of the tree is going to be more.
Okay.
And then what you're trying to probably achieve is go back to that particular level where.
But I'm not, right? I'm not changing my tree. I'm just relabeling the leaves.
And relating to what?
To some other label. We agreed every leaf has a single label to it, right? This is the answer. I'm changing the answer.
You're changing now.
Yeah, that's it. I'm not changing the topology of the tree. Yeah.
Optimization problem looks like knapsack.
In fact, it is. This is knapsack.
Yeah. Which is a hard problem.
Yes, but an easy hard problem. You know, among all the NP hard problems, knapsack is one of the more friendly ones, right? The other one's bite. This one is kind of just gives you a little nibble. Because you can actually you can approximate knapsack pretty well. You look so skeptical. You don't believe me? I mean, NP hard problems are personalities, right? I mean, knapsack is a very friendly personality. It's like it's hard, but it doesn't really want to be hard. Whereas click is like, I'm hard and get out of my way. You know, they have different personalities. So, you know, knapsack is nice, friendly. So this is not a bad thing to have. So, but this is true. This is a knapsack problem. How many of you have heard of the knapsack problem? Okay, good. Most of you have. So, and the knapsack problem, as just remember, you have a knapsack. You're a thief in a gallery. The alarm's gone off. You want to get as many pieces of jewelry as you can, but you have a small backpack. So you want to maximize the profit, but the backpack is only so big. So you have this trade-off between profit and how many things you can actually carry, and that's what you have here. So basically the summary of the solution that in this case, these two are easy. You just build a tree here. You build a tree using this weird other measure, and then relabel using a solution in knapsack. And like I said, what's surprising is that this actually works quite well in practice. Something that I'm hoping we can explore a little bit ourselves in some actual tests and see. Okay? Okay. Any questions? Yep. Okay. So what we're doing here is this, right? So go back to the decision tree problem here. We're saying that every time we pick a leaf, okay, so let's see how to say this. Okay. So this is our desired bias threshold. Okay. This is where our decision tree is right now. Okay. This is the amount of bias we have to reduce. Every time we change a leaf, we hope to get some reduction. Right? So of course some cases it might get worse, but so let's say you get so maybe you pick the first leaf, you get this much reduction. You pick another one, you get this much. Maybe you pick another one, you get this much and this much. But in the process of doing so, this is our current accuracy, right? The process of doing this, our accuracy is now, every time I pick this, our accuracy went down by that much. We picked this and the accuracy went down by this much. We picked this and it went down by that much. So we're trying to get down here without paying too much of a price here. Okay, so what does it have to do with knapsack? If you think of this as saying, I want to get at least this much weight, right? So let's say this number is, I don't know, W. Okay, so you want to pick items whose profit, right, is at least W. right? Now think of this as a cost. Think of this as a negative number. So I mean, well, think of this, yeah, this profit is W, and you want to minimize the cost. So the way to say this in terms of in knapsack is to say, in knapsack, so profit is at least W. You can think of as, you flip it around as minus profit is less than or equal to minus W, okay? Now you're saying I have a knapsack, imagine a knapsack of negative height, and I'm putting negative things into it, and I don't want it to be too big. So that's my knapsack size constraint. Again, this is a minimized cost. This is also like saying maximize minus profit. So now my accuracy things are the value of my jewelry in negative sense, and that's what. So that's by playing this. That's what I'm saying. By playing with positive and negative signs, you can transform this in the knapsack. Straightforward exercise to do that. Okay. Any other questions? No. Okay. All right. So this is our first that we've seen of a technique that bakes the design of an unbiased decision-making system into the classification process itself, right? With a decision tree and with statistical descriptor. Okay, all right. So let's move on to the next one. And I believe you may have seen some of this already. So you covered the three naive-based approaches to. Yeah, but you did a little bit of it. So you covered basically the naive-based sort of argument, right? Yeah. Okay. Okay. Good. So the next approach, which is, has another sort of way of thinking about this problem. Again, what is the model? The model is naive-Bayes. And again, the goal is to get independence. I'll put this in quotes because it's not, well, they actually, no, they do use statistical discrepancy here. So I'll write it down for you. So we're still doing classification, but now we have a different model. Okay. So you've all have seen from the first day, or probably have the basic naive-Bayes setup. Have we seen a naive-Bayes setup from the first day? No. You didn't cover it at all. Okay. So how many of you have heard of naive-Bayes? Oh, much larger number. Interesting. So okay, good. I'm going to be lazy then. I want volunteers. Someone tell me how naive-Bayes works. Abhishek, I saw you had your hand up. So why do you start?
I know a use of that in the bag of words.
Yeah, that's fine. Let's do the bag of words example.
So we basically calculate the frequency of words in the bag and.
So let's back up a second, right? So what is the goal? A goal again is to classify.
To find a pattern.
But to classify, to label something, right? So you have a label. So you're given a point, and you want to find some label.
Yeah.
And this is going to be a kind of you're actually going to get a set of probabilities. And often you'll say, okay, so I'll get a set of answers. So I'll say there is a probability of it being in class I for all I. And then I might say, okay, pick the best one, right? So the label for X is equal to the arg max probability of Ci given X. That's right? Right? So the naive-Bayes classification gives you a little bit more information than just say a binary answer. The goal is to get some kind of distribution over possible answers, and then you can choose how you want to pick. You might pick the best one, or you might pick whatever you want. Okay? All right. So good. Let's continue. So we have this setup, and we want to build a naive-Bayes based classifier. So let's say the bag of words. So what is the bag of words task? What is the goal there?
So basically, the basic goal is to classify, and
Yeah.
that has to do with the frequency of words you can get in that bag of words.
Yes, but how? So what is the key? So in other words, so this is called naive-Bayes, right? So clearly Bayes has to appear somewhere in the game.
Finding out the probability given the
Sorry?
Yeah, he's already written whatever he said.
Have I already written? Yeah, well, that's part, yeah. So anyone, we had a lot of hands coming up here, so don't just watch Abhishek score, someone else, yeah. Let's say you have two classes, so we have C1 and C2, okay, good. Well, you want that. You want to calculate that, so you can label X appropriately. But that's the goal. How? So P of C1 given X, P of C1 intersection X, yeah, by P of X, yeah. This is nice algebra, but how does it help us? Why is this a good thing? We've just gone from this to that. So?
Because there are a number of attributes. So it says that it assumes that all the attributes are independent.
Yeah.
They do not depend on each other. So that's why we can write it in terms of like joint
So you're saying this can be written more easily?
is a product of all the marginal probability distribution.
Okay, so the claim is that somehow this object here is easier to compute than this object. This object is what you want, but by using Bayes' theorem, we get this object, and this object you should think of as X as some kind of vector of things, like a bag of words, you have a sort of set of things. So if you think of X as equal to X1 through Xk, that's like a sequence of things, then you can write P of X given C1. So we already covered the Bayes part of this argument, now we're going to cover the naive part of it, which basically says we can rewrite this as an independent combination of the corresponding ones here. Namely that P of X given C1 is the product of P of Xi given C1, I is equal to 1 to K. Okay, this is more algebra. How is this helping me? How is this helping me at all?
Because this is creating the biasness in the system.
No, there's no bias yet. I'm just talking about basic naive Bayes classification, right? There's no bias yet. How is this helping me?
You can get PXI of PI from the data itself.
How do we do that?
Calculating the frequency.
So, what is this? This is the probability of Xi given a particular class. This we can get from the data. We can look at frequency counts. Right? So we can look at frequency counts in the data and compute these quantities. And that's where the naive Bayes approach comes from. You have the Bayes and the naive. The naive part is by saying, oh, we will assume that everything is independent. This is a naive assumption because things are not independent. But it's a good enough assumption for many problems. In fact, at least for a long time, the best methods for detecting spam in your email were based on naive Bayes filtering. There are slightly better methods now. But naive Bayes is still a very successful tool. It's one, in fact, if you take a machine learning class, this is often taught as one of the examples of where naive Bayes works very well, spam filtering. So you just take a bunch of words, take this part, and put them together. Okay, good. So we have a naive Bayes classifier, and we can compute these numbers here, right? And now we built our classifier, and now we have some potential bias in the classifier. What should we do? So in particular, what we're concerned about is that we have these numbers here, right? And we know that, the probability of C1 given group 0 minus the probability of C1 given group 1 is too big. And we want to fix this. How do you do that? How might you do that? Thoughts? So one way to think about this is this, well, this is equal to this, right? If I don't like this, I should probably change something here, right? In particular, this is a part of these things, and one of these is my sensitive attribute. Maybe I should change some things here. How would you do that? So in particular, let's say you have some particular sensitive attribute S, and you have this whole product of things. So this is basically equal to product of S given C times the product of, P of, let's say AI given C, where these are AI, A1 through AK are the other attributes. This is equal to P of X given C, right? So this thing is this product here. I just took out the one term by itself. Right, and so one reasonable strategy you could adopt here is to say, if I have these numbers and they're kind of messed up, I want to change these numbers somehow. You want to reweight the probabilities of the probability of seeing this attribute given this class label. So you update the probabilities. Essentially what this means, essentially what this would mean is that you have your table, right? And you have your data in it, and you evaluate these probabilities based on weights in your data. So what you do is you basically look at examples where in your classifier you give a 1, or you give a 0, and you give a 1. You look at all the things where you gave a 1, right? And where you had the sensitive attribute. So let's say the sensitive attribute, we should probably call it G, I guess. Sorry, call it G. So where this was this number was very small because this number was too small, this number was too big, let's say. So you want to give more probability to items that have the thing that look like that. And then you build your model again, right? So you change the weights, essentially, of the items, which the classifier is predicting, as the classifier is labeling, and you just update the weights and you start all over again. So this is one simple strategy you could adopt, literally you can increase this by increasing this. And one problem that they point out with this strategy, this is one of the things they try to use, but the one problem they point out is that what that will effectively end up doing is changing the total number of decisions made in the process. So imagine that, and this is the example they give, suppose you're giving out loans in a bank, right? So these are decisions for loans. And you have some bias and you're worried about that and you want to fix it. And you fix it by increasing the probabilities of items where your thing was, by increasing the probabilities of cases where you had a 0 here for the group and you had actually a good decision for the outcome, or vice versa. Decrease the probabilities for a 1 and a 1, right? But then what's going to happen is that depending on the fraction of attributes, fraction of tuples having a 0 or a 1, you might increase or decrease the total number of loans made once you rebuild your model, right? Because by increasing these things, you're saying, in this case, okay, give more loans out. And this, by decreasing this, you might say, well, give fewer loans out. And you might end up with more or less number of loans given out. And this may be something you don't want to do, right? So this is something you could do, but something you may not want to do. So the question is, can you somehow update your model to be unbiased or less biased, while at the same time making sure that the total number of decisions you make does not change too much. So you still have the same number of decisions made, you just kind of redistribute the decisions in a different way in order to be more fair. So if you do give someone, you balance things out the right way. That's the question they want to ask, okay? So, let me see. Right. So the subtle change they make. So one way to think about the naive-Bayes model in a sort of a more graphical model sense, in other words, in terms of understanding the relationship between variables, is to say that we have some class variable C, and this seems to depend on A1 up to AK, and of course S. Right? And when you write something out like this, since these are all independent, you can look at this diagram and say, okay, the probabilistic model that generates C can be written in this form because of the independence properties. right? So that all of these things are independent. So you can write down the entire joint probability distribution of these things as the conditionally independent probabilities of this times that, which is basically this. Okay, so a graphical model is a nice way to compactly represent these kinds of distributions. The change they propose is to do this, is to say, look, we don't want to have to tamper with these numbers because it might change the balance. Let's change the graphical model, the way we think about the data being generated itself. So you remove this edge here. And you change the direction of this. In some sense, what you're saying is that the sensitive attribute appears to be controlling the class label, which is then controlling the other things. So the way you write down your distribution now looks something like this. So instead of when you want to write down the joint distribution of C and X, right? Instead of just writing as this, it'll be basically P of C1, P of C, sorry. Sorry, no. So it used to look like this. So your thing used to look like this. You have some P of C, and then you have P of S1 given S given C, P of A1 given C, and so on. Just the way we wrote it here. Sorry, G. I keep saying G. Okay. And what you do by replacing this is that you're saying we're going to write this way. This now becomes P of S, P of C given S, and then the same stuff as before. P of A1 given C, and so on. So in other words, we've changed the generative model from our data, or we're proposing changing the generative model of our data from a model where all of these are conditionally independent with respect to the class label, once you have the class label, to a model where the sensitive attribute is treated slightly differently from the rest. Right? But the sensitive attribute is sort of controls the whole process. It's defined first, you get the class label, and then once you get that, you get the whole thing.
How are you getting the sensitive attribute?
That's always the one that's given to you. You're told, right? I want my loan making to be not racially biased or not be biased based on caste. So that's always given to you. So in everything I'll be talking about we're always told this. In fact, the problem of, what do I do if I don't know what the thing I'm being if I don't know how I'm being discriminatory, how do I figure that out? That's actually a different problem itself. It's kind of an interesting and tricky question. I haven't seen any good answers to that question. It seems hard. I mean, so you could be discriminating against anything, right? I mean, you could be discriminating against people who are, very bad at math by failing them. But is that a bad thing? I don't know. So maybe that's a bad thing, right? So, yeah. So that gets. So you're always given this thing, right? So you're given that. Okay. Again, I should keep saying G. Okay. Okay. So the proposal they have, in order to get around this issue of I don't want to change my probabilities because I might change the total number of decisions I make, is to subtly change the way they think of the data being generated, right? That is being generated first by essentially picking the group label, which controls the class label, which controls everything else. And now the question is, can you reconstruct the labeling from that data? Okay? And so then what it turns out they can do is, rather than, so if you now think of what this is going to look like, right? This is going to look like this. P of C given X, using the Bayes trick, is going to look at the joint distribution, P of C and X divided by P of X, right? But now this can be rewritten in this form, which is and the same as before. Okay? The only difference is that you've gone from this to this. Okay? And then what they say is that they essentially modify this information in the data. So they have this table in there, and they have an algorithm in the paper which does some small increments to these probabilities in the data. So you have, again, your tuple, and you have your C's and G's. You adjust the weights a little bit that way to rebuild your model. And once you do it, you keep doing this as long as you build a model, you check the discrepancy in your model. If the discrepancy in your model is bad, then do this again by updating the things a little bit, and then so on, so on, so forth. So it's a small change they make. It's not a significant change, but it's a change that allows them to keep balance on the total number of decisions that are made while still testing this out. And again, if I can figure out how to get this, it'd be fun to actually play with this and see what happens when you do this versus that. So we'll see if we can do some experiments with that.
Why are we allowed to change P of P of Q and P of Q?
The claim is that, and again, I'm not fully convinced I see it either. But I think the claim is that by doing the modification this way, you can still keep control over the total P of C. Essentially this quantity here. That's the idea, which is really what you want. You want to keep this fixed, the total number of positive decisions that are made. And that somehow by flipping this, you can do that. Well, because, okay, so in either of these strategies, the way to decrease bias is to change the labelings, to change the weights you increase the weights of things you want to encourage. So in this case, you want to encourage group 0 to have a positive outcome. So you increase the local probabilities on these events. You change the weight associated with them, right? So that in any method you use, you change the weights of the tuples and rebuild your model again. So you run your model, I think, and this came up actually yesterday. There was a suggestion that you can build your model, look at what's happening, change the thing, rebuild the model again. I think when you're talking about modifying, you had mentioned this, and I said, okay, we'll get to that. But now we're getting to it. So that's the idea. You sort of take your model, see what it's giving you, rebuild it, and then do it again. Much like what we did in the previous example where we looked at the labels, we looked at the results, oh, there's bias, and we changed things around. Of course, there we didn't rebuild the model. Here we're actually rebuilding the model again. That's the difference. Can you? Can we break for T? Can we break for T? Yes, I think the vote is for break for T. So let us break for T. We'll come back and talk more about this. Okay. Thanks. We were talking about the naive Bayes model and how to introduce an idea of fairness, and so I described at least one idea to sort of tweak the weights of entities, essentially, of tuples, by changing the way we think about the generative distribution describing the data. And I think there's a sort of maybe a 1-minute digression here. One of the problems with a lot of the work around this area, in fairness, is to say, well, all you're really doing is finding some kind of correlation. That doesn't actually mean that there's any actual bias of any kind going on. There could just be some accidental correlation. And in many ways, this objection is fair. Oh, I had my correlation is not causation t-shirt. I didn't wear it today, but anyway. So one of the efforts in this area is trying to think about the problem of bias from a causal perspective. And if you've never looked at causal analysis, understanding causality is one of the deepest and hardest question in all of data science. Again, one of those questions that goes back 1,000 years, thousands of years, just asking the basic notion of what does it mean for something to cause something else. And it's been studied in economics, it's been studied in machine learning, it's been studied everywhere, but to this day, we don't really have a good, solid technical foundation. We have many of them, but we don't have something that we can work with to understand causal relationships between variables, especially when we're just observing data and we have no control of the data. When you have a randomized control experiment, then you can actually determine causality. And that's how the medical world proceeds. But we don't have that luxury in just arbitrary data collection problems. And so the idea that you should look at causal structures, or at least graphical models that might generate the data, is an interesting idea. I won't be able to say much about it because there's not much to say, unfortunately. But there have been So there's a growing interest in trying to use causal structures in machine learning in general. So I mean, forget about this topic of this course. Just for machine learning in general, I think if there's one topic that you might find useful to study that really no one has a good handle on, and that could give you some sort of powerful tools to play with if you understood them, then studying causal analysis might be something worth thinking about. Okay, so causality and causal analysis. At least one person has got a Turing Award for his work in causality theory, Judea Pearl. I mean, he's for graphical models and for causality, among other things. And people from economics who do causal analysis all the time because they want to say, okay, what happens if we do demonetization? How is this going to affect the economy at large? Right? There are people in the RBI and other who will be thinking about this kind of questions. They are actually going around to machine learning conferences telling people in machine learning, hey, you should think more about causality and you should give us tools that we can use because we need better tools for doing causality in data science. So just as something to keep in mind for the future. Causality has always been something that's in the future. It's still in the future, but the future may be closer than one might think. So if you get a chance to study causality, I strongly encourage you to take some time to do it. Read Judea Pearl's book or read some other books on this topic. So I'll write down Judea Pearl's name. He's one of the computer scientists who's worked a lot on this. There are lots of other people though. It's a huge area. And there are lots of nice work on this. Okay, anyway, that was my maybe more than 1 minute digression, but okay. So coming back to the thing here, the reason I went off on this digression is also because if you notice the way we changed the way we wanted to think about this modeling process was to change the graphical model that described the way the data was being generated. And this paper basically does this in 3 different ways. This is one way they do it. Another way they propose to change the underlying graphical structure can be thought of in the following manner. If we're worried about building models that are biased, let's say in this case based on gender, then why not just build one model for one gender and one model for another? So you have a data set, it has information about males, it has information about females. Why not just build 2 separate models? So you think of your data set as split up, right? So you have so you build model M1 from here, build, let's call it M here, and MF here, and then when the data comes, depending on whether the person being considered for the loan, let's say, is male or female, you run one model versus another. And again, you can express that intuitive idea in the context of a graphical model by saying that we had this attribute G, which was pointing to all the other attributes. We can also think of G as pointing to all the other attributes as well. Essentially, what this means is that for different values of G, you have different graphical models themselves. So you have the G equal to 0 model, you have the G equal to 1 model, and so on. Okay? And so this is a very simple idea that anyone can actually try. You can say, okay, I'll take my data set, split it by the values of the attribute, and then run different models. Now, there are potentially legal issues associated with this. There are, at least as far as I think, you would not be allowed to do this in the US. You would not be allowed to have one procedure for men and one procedure for women. This will not work. You have to have the same procedure for everyone. So there are potentially legal ramifications of doing this. But just conceptually, as a data mining problem, you could say, well, why not just build models this way? So they test this out in the naive Bayes setting. So they take their naive Bayes classifiers, they build one naive Bayes classifier here, and they build one naive Bayes classifier there, and they look at the statistical discrepancy they get with respect. You might still get some, when you combine these, you might still get some overall discrepancy, but the hope is it'll be much less. Okay? So that's another interesting trick that you could actually use in other models as well. Okay. The paper actually talks about one more model, which is called a latent variable model. I'm not going to talk about that here. I'm going to skip that. Okay. All right. Any questions before I move on to the next technique?
Mine's still a separate but equal thing for the segregation period.
Kind of just, you just killed this whole idea by giving it that insulting name. But yes, you're right. It is, so this whole, there was this, I guess separate but equal applies not just in the US, but also in South Africa, the apartheid sort of time. the idea of separate but equal was that after the Civil War, basically the whole point was that that we should be treating the African Americans and the whites sort of the same way. But this whole doctrine of ideas came up through some somewhat misguided decisions that allowed separate treatment as long as they were equal. So as long as the white students had a school and the black students had a school, they were treated equal. Of course, in practice, what would happen is the school for the white students was rich, was well funded, had good education. The school for the black students was not. But they were both schools. And so it was okay. And then over time, what happened was, no, this is not acceptable. The separate but equal is not going to work. And you have to have a proper integrated way of treating both groups. Right? So you could argue that, the problem here could be that if you do this, then, yes, they're built separately, but maybe this model is built very badly. This model is built very well. So this model, makes really bad decisions. This model makes good decisions. And now you have another problem. So in some ways, doing this doesn't solve the problem of bias unless it's done correctly. It just kind of pushes it off to the side. So that's an interesting observation about it. Okay, I'm going to erase this now since we seem to have no more questions. So we've seen two scenarios so far, right? We saw decision trees, and we saw naive Bayes. Both specific models for learning where we wish to instrument the model with some ideas of unbiasedness. And as I said, in at least today's lectures, we're going to be looking at specific models in each case, while trying to draw general ideas from these specific models. The third example we're going to look at, and I'll look at a bit more briefly than the other two, is the idea of logistic regression. So let me get to my notes. So you've all seen binary classification, and of course regression is the generalization of binary classification to the case when you have multiple, sort of a smooth output, right? Instead of output being 0 or 1 or one of a couple of classes, you have a continuous variable output, right? And so logistic regression is one kind of regression model that you can build. I am not going to talk about building the regression model itself. I'm going to limit myself to saying that basically the way you build these kinds of models, the way you do SVMs, is you have some cost function. So you have some parameters of the model, okay? Usually something like this. And typically, let me see if I can write down, hang on one second. Yeah, okay. So basically you're trying to predict some score between 0 and 1 in this case. And typically you predict it using some kind of sigmoidal function. So you have some kind of theta parameter and you have some kind of sigmoid. So you something like, so let me see if I can get this right, make sure I don't make a mistake. So a sigmoid, okay. Someone remember what a sigmoid function is? 1 plus e to the minus lambda x? Yeah, okay, good. So, and the property of a sigmoid function is that it looks like this, right? So basically if this is 0, you get 1. If this goes to, if this is 0, you get half, right? Because 1 plus 1 is half. If this goes to infinity, you get 1. If this goes to minus infinity, you get 0. So this curve looks like, like this. I drew this badly because of course it asymptotes at 0. It doesn't actually hit 0. So, right? Yeah? Well, okay. Well, you get the idea. And this is half right here. Okay? So, idea is the point of a sigmoid is you want to convert a variable that's can range from minus infinity to plus infinity to one that ranges from 0 to 1. And the lambda is just a scale factor to see how quickly this transition gets made, right? If you make lambda very large, then essentially you're going very quickly from here to here. So it looks more like this. And you make lambda very small, it's like, I'm just going to go lazily to there. Okay, so that's how so the lambda parameter is a controller. And the way you think of logistic regression is that if you think of this as a sigmoid function, so you can think of this as sigma x, okay, as defined as that, then the logistic regression basically says that you are, you want to find some parameters, right, so that sigma of theta transpose x gives you the class label that you want. So you want this to match your class label, right? So you have to scale this. It depends if your classes are -1 to +1, you modify the sigmoid to be, instead of between 0 and 1, between -1 and +1. So you basically multiply it by 2 and add 1 to it. So there's a bit of scaling that goes in there. But that's basically the idea, that this is a parameter that controls your regression problem. And the way most of these problems get solved, logistic regression, SVMs are no different, that you basically have some kind of cost function. So it's over all data points. You look at yi and you look at sigma theta transpose xi, and you have some other cost functions there, and you want to minimize this over all theta, right? So I'm just going to put some gigantic cost function here. The details don't matter. Okay? And the theta that you find is the best theta for your problem. And so the reason I'm willing to hide all these details in this paper is because I just want to focus on this. That this is, an example of what is called empirical risk minimization. You have some kind of risk or loss function, a penalty for using that model to classify that point that particular way. And so you write down the cost for all the points and add them up. And maybe take an average or take weights if you want. And you want the one that minimizes this overall cost. It's a very simple optimization. There's a lot of machine learning right now is just write down the cost function and optimize it. So there's a lot of work in machine learning that's really just work in optimization. Because someone gave you the cost function, now the goal is to do the hard part is the optimizing part. Find the minimum theta that does this. But the point of writing it this way is to then realize that if you want to add in more constraints, you can fold them into this optimization via this process of what's called regularization. And regularization, of course, is a fancy term for adding some extra function here, some regularizer. Okay, which is usually a function of just the parameters, not of the data. And what is the intuition for this? So how many of you have heard of Occam's razor? The principle, at least. So the principle of Occam's razor, I forget the original Latin, but the basic principle is don't use a complicated explanation when a simple one suffices for the data. Okay? Which is not to say that simple ones are better. It's just that, if you have a choice between two and one can explain the data and one explains way too much more, then start with the simple one. And Occam's razor shows up in machine learning a lot because you can say things like, well, I want a model that fits the data, but I don't want an overly complicated model. I don't want to overfit. And one way you can think about how not to overfit is to add in a term like this. You all did this lab where you're doing cross-validation, and some people are asking me about why that C parameter is there. That C parameter is one way of controlling the complexity of your classifier and whether you're going to overfit or not. Right? If you're overfitting, you're using too complicated an explanation to explain the problem. So this comes into the general class of regularizers, but the word regularization has been now overused to mean any other kind of function you might add to the cost minimization to achieve some desirable goal. Okay? And the reason I'm saying this is because now the desirable goal here is going to be to use this idea to achieve unbiased. Right? So in fact, the title of the paper is Fairness-Aware Learning Through Regularization. So this is the idea here, the big idea, if you wish, that you can take away is one way to think about how to inject fairness into a model building process is to add it as an extra regularized term. And I don't know if you ever, many of you have probably read lots of papers in machine learning, and a lot of them will look like, here's a cost function, here are the 5 things we want to ensure as well, here's a regularizer for this, here's one for that, here's one for that, here's one for that. Gigantic minimization, throw it into a solver, declare victory, go home. And we'll see one paper a bit like that later on today. But it's much more clever than that. But it does have a bunch of different terms it wants to balance, and I don't know, we'll just throw them all in and minimize some gigantic function and do cross-validation to find these parameters. Okay? It's a good, again, as a sort of general data science trick, it's a good trick if you have a bunch of competing objectives and you want to build a system to balance all them out. It's a good, quick and dirty way to get something more going. And then you can tweak it if you want. So here we're going to tweak this thing to do fairness. So then the real question is, how do you inject a regularizer into your minimization so that you can achieve those things? So when you do this, of course, you're never going to say, well, I'll guarantee to get fairness, or you're not going to, or guarantee to get optimality. You're not going to guarantee any of those things. What you're saying is that I want to balance out my concerns, and this parameter will balance them out. I can always tune this parameter to be more or less worried about one of this or one of that. Okay? All right. So here's our question. How do we regularize with respect to fairness? And the way we're going to do this is to introduce an idea of a nice information theoretic idea to capture a sense of bias. Now in this paper they call it prejudice, but it's the same concept. So here's the idea. So once again, we have the data, and if we're working with logistic regression, usually you have some underlying distribution over the data. So it's a probabilistic model. So we have the class variable C, as always, and we have this sensitive attribute S, right? And we build some classifier when you get some answers for the class variable. What we've always said, right, in all of our different ways of thinking about discrepancy or mutual information or information gain that we saw with decision trees is that there is potentially a problem of bias if there is a lot of information flow between these two things, right? For example, if I could predict this from that, then there's clearly a problem of bias. Or there could be a problem of bias because now this is being controlled by this variable when it probably should not be. And yesterday we talked about how to formalize the idea of information flow in terms of entropy and mutual information, right? Or at least, well, I kind of hand-waved that a little bit. But let me try to formalize this idea a little bit more right now. And as I say this, I realize maybe I should, since when I polled the audience, not all of you were familiar with entropy. I'm pretty sure even fewer of you are familiar with mutual information. How many of you know what mutual information is? Right, that's what I thought. Okay, so we've seen entropy as a measure of information content of a distribution. There's also a formal way to capture the idea of information mutually held between two variables. Like how much information content do these two variables share, two random variables, okay? And that's what's called mutual information. And I was waxing eloquent about this at lunch yesterday, but I will say this again here in class. Another thing that you should definitely do if you want to study data science, right, is study information theory. You can't go wrong because information theory is the mathematics of information, and the very fact that you can quantify information is just so cool that you just have to read it just to appreciate that. So there's a very nice book by Cover and Thomas, and I strongly encourage you to go out and find it. I know for a fact that there are sort of reasonably cheap Indian editions of this book because my cousin has one of them. So, and so you can find a good one, and this is really a good book to read. You can just read it like a storybook from cover to cover. It's just awesome. Okay. So, and a lot of this shows up in machine learning as well now in ways that we're learning more and more. So, and it has always been there, but that's why it's important to learn. So, mutual information is I'll define it for you. So, suppose you have two variables x and y, and they have some joint distribution, right? So they're not independent of each other. Okay. Since they have a joint distribution, but they're not independent of each other, there is some shared information between them, right? So so the probability of seeing one and the other is something that relates to both of them. It's not just dependent on one or the other. In fact, the definition of independence is that this is equal to this times that, right? This is the very definition of independence. The probability of two events is equal to. And the reason this mutual information captures the opposite of independence, because it's saying that no, to figure out whether both these things are going to happen together, it's not enough just to look at whether this happens and whether that happens. There's some other magic going on between them that either makes them more likely to appear or less likely to appear. Right? It can work both ways. Right? Negative correlation or positive correlation. So how do you quantify this idea of distance from independence? This is what mutual information is trying to capture. How far you are from being independent. The further you are from being independent, the more information you have with respect to each other. The closer you are to being independent, the less you have. So ideally, you want this case to correspond to the mutual information is equal to 0, because there's nothing between them, and you want something else. So it turns out there's a simple formula that will get you exactly what you want, and it looks like this. That the mutual information between two variables, and this is symmetric. It's not an asymmetric, it's not like conditional entropy or something. So I'll write it like this, right? And I'm abusing notation a little bit here, but I've been abusing notation so much in this lecture, so you won't even notice the abuse here. So it's a double sum over x and y, or an integration if you choose, of the, let me write this up. Okay. You might wonder what this weird thing is. It kind of looks like an entropy, but not quite. It's got this weird stuff in it. What this is, in fact, is another wonderful concept from information theory called the relative entropy, or the Kullback-Leibler divergence, or it has other names. I'll just call it the Kullback divergence. It is a distance function. I'll just call it DKL. This basically corresponds to a distance between the joint distribution, which is Pxy, and what you would have if it was truly independent, namely the marginal distribution, the joint distribution appearing if they were independent. Where this DKL for any two probability distributions is asymmetric, so I'll actually put a little bar here, and is equal to the sigma over all I, pi, the probability of the ith item, log pi over y. No, because it's not because, because it's not, because the way you set up the whole thing, that's right. So the mutual information is a distance from the joint distribution to the distribution you would get if you took the marginals and made an independent joint, a joint distribution from the marginals. If this was actually the same as that, then this distance would be 0, as it should be. The further away it is, the larger this number gets, and that's what mutual information is. Okay? So mutual information is a very wonderful beast, and I could spend many hours talking about it, so I won't do that now. Not sure I follow. Not sure I understand the question.
The joint distribution would be 1, only in the case when the both distribution would overlap each other.
No, the joint distribution, so okay, this is where my abusive notation might be hurting me. So when I say p x comma y, what I really mean is the probability that the random variable is equal to x and this one is equal to y. This is the set of all numbers for all small x and small y is the joint distribution of these two variables. Think of it like a table. So I have some kind of table. I have all the different values of x. I have all the different values of y, right? And in each cell I write down, okay, what is the probability that I see x equal to xi and y equal to yj. We'll call that number pij, okay? So this matrix is the joint distribution of x and y. If this matrix is independent, if these variables were independent, then this matrix could be computed as the rank 1 outer product of the marginals. So this would be equal to p of x, p of y. This is the case when they're independent, right? So in either case you get a matrix, but in one case the matrix is formed by a rank 1 outer product, in one case the matrix is just a general matrix. The distance of this matrix to that matrix as measured by the Kullback-Leibler divergence is the mutual information. I feel like the collective atmosphere in the class is sinking down to the ground. It's like, oh my God, what have we just done here? Take a second to sort of register this thing. Again, and if you haven't seen this before, this is a slippery concept. It's not a concept you just get in 1 second. It's taken me years to fully, feel the love of mutual information within me. And, I'm trying to share that love with you, but it'll take a while. So, it's not an easy person to get to know, but it does take time. It's not going to come immediately. So if you want to, just merely understand the formula and the fact that it captures distance from independence. That's enough for now. And it also more metaphorically captures the amount of information content between two variables. That the larger this number is, the more they share information. The more you can infer something about this from something about that. Okay? Because intuitively, if they're independent and I see this value, it tells me nothing about this value. But if they're not independent, if they're dependent and I see this value, it tells me something about this. And that's exactly the concept we want, right? Under what condition does seeing something about the class label tell us something about the sensitive attribute? And that's why we want this language here. So this mathematical language is the right way to express this idea that we want from here. Okay.
Then this converts to something nice in case of multivariate normal distribution.
So wait a second. So say it again.
Say we have a multivariate normal distribution.
So you have two.
Yeah. So they make the formula very nice. So like they have normal distribution one where there is normal distribution that's the covariance matrix.
Yeah.
So does that like is mutual information? Is there like good correspondence between the mutual information and covariance distribution?
So I've never worked this out, but my guess is that the answer would be something very clean and would relate to the covariance matrix. Is that what it is?
We can compute the mutual information using covariance.
Yeah. So basically, intuitively, if the covariance matrix was identity, then these are actually disjoint. They're independent of each other because Gaussians factor out. Right? A two-dimensional Gaussian distribution with an identity covariance matrix can be written as a product of two one-dimensional Gaussian distributions. This is a very nice property of the Gaussians. So in that case, they're independent. So the degree of independence directly relates to the covariance matrix. Yes, and I'm actually glad you brought this up because this intuition is going to come up later today. I was wondering how to bring it up, but then you brought it up from yourself. This is great. So that the relationship between mutual information and covariance is going to come up later. But yeah, there's another comment. Well, not the same, but it's used to. It can be used to compute. My intuition is that, and that's what you're saying, that it can be used to compute the mutual information is a number, right? Yeah. So the mutual information is a number. It's a single number, right? I see a good final exam question here, right here. Okay, so where was I? See, I lost my train of thought. Okay, good. So, can we use mutual information to put, remember, what is our goal after all this long digression? We, yeah, yes.
We have used the same method in order to develop one new algorithm for clustering.
Oh, please tell more.
I cannot tell right now, but I
Darn it. Okay.
But I will.
We can have one seminar for you. No, we are planning a
So,
seminar for you. We can request Dr.
we have changed this with the covariance matrix and we got very good results.
Ah, okay.
I'm having that.
Because it's easy to compute the covariance matrix.
Yes,
Yeah.
There are many more things, but somehow I will.
Excellent. In fact, one of the papers I will talk about later today, they use a very similar idea to that. They want to capture some mutual information, but the covariance matrix is easier to work with, so they'll work with that instead. And so, I was reading this paper, I was like, why are they doing this? It took me forever. Finally, I realized, oh, okay, they're trying to approximate the mutual information with this covariance idea. So, yeah. So it's not an obvious idea, but it's, yeah. Okay. Well, it wasn't obvious to me. Maybe it's obvious to me. Okay. Okay, let's get back to our regularizers. Remember, what is our goal? Our goal was to say we are building a model, in this case a logistic regression model, but that detail in this case doesn't matter. But we're building it by basically minimizing some cost function over the choice of model parameters. And we want to add in a term, which we call a regularizer, that will somehow balance out the minimization so as to emphasize the importance of being unbiased. Which means that somehow this function here needs to encode the degree of bias in the system somehow, right? So if you want to minimize this, you want to decrease the cost and you want to decrease the amount of bias in the system at the same time, and there's some balance between them. And so that's exactly what they do. They, this is what they propose to do here. So what they say is that we have, again, going back to where we came here, we had the class label and we had the sensitive attributes. In a probabilistic system, you can think of these as random variables. There's some underlying probability of class label being 1, there's some underlying probability of class label being 0, and there's some interaction between all these variables, right? We talked about this in the case of the graphical model as well. And so, if we want to measure the amount of information that's being transmitted between the sensitive attribute and the decision, so how much is the decision being influenced by the sensitive variable? We now have the language to think about this. We now have the vocabulary coming from mutual information to think about this. In particular, we can say that the mutual information between the classification output and the sensitive attribute treated as random variables is a measure of what they call prejudice in the system. Okay? And so if you write this down, so this becomes a summation, probability. Remember I was holding here, we wrote this down here. Right? And so the trick is going to be that some of this can be expanded out. So you can write this as let's see, one way to say this is let's see if I can say this correctly. Yeah, so So this corresponds to the model parameters. So I'm going to write the model as M. The model output given S and X and theta, where X is all the other variables that we're not concerned about, times the probability of, let's see, so we want Sx, right, yeah, times all this other log stuff here. Okay, why am I writing all this out? What I want to show you is that if you now write down this measure as this mutual information, which you now expand, what this is doing is it's introducing the model terms here. Remember, what is my goal? My goal is to take this whole expression and put it in here. And this needs to be a function of the model parameters. So what is saying, well, this is my model, my predictive model that I'm trying to find. The predictive model takes my input, takes my model parameters, and produces a prediction for the outcome. So it depends on the model parameters in some particular way. So if we take this whole expression and put this in here, we now can minimize over this whole thing here. Okay? So you are able to encode the idea of bias as a function of your model parameters, so that now you have this gigantic minimization that you can now minimize. So I'm not actually going to give you the details, because the details are not as relevant in this case. You're not going to implement this right now. They're not as relevant as the idea of putting the regularizer in, and the idea that mutual information can be used to encode bias in this manner here. Because otherwise what would happen is that if you try to encode bias just using your statistical discrepancy, for example, it would be much harder to nail down precisely how the model parameters are affecting the final outcome. It's a little bit harder to write that down. In this case, it's pretty straightforward to write this down. I'm not actually sure that's correct, but anyway, that's what, yes.
This is a classifier.
Yeah.
So,
It's a logistic regression. Yeah. So yeah.
so one fine. So we are doing about the same thing as we were doing in decision tree, where we were adding the attribute information gain
Yes.
to the total, the objective function.
Yes.
So in this case, do we need, I may be wrong, do we need to do some relabeling and then?
So the question is, just like with decision trees, it seems like we're adding some kind of regularizer term. There also we add this extra term. But in decision trees, the argument appeared to be, oh, but do this and at the end fix your problem some other way. Would we need to do that here? It's not, at least this paper doesn't seem to think so. Huh?
We don't want answers to the paper, we want your views on this.
I don't know. I don't have a good intuition for this. This whole business of should you be relabeling at the end, I have not spent much time thinking about it, because I've always thought this whole change the output was a little questionable.
Your first thoughts?
My first thoughts on this?
Well, I'm not going to leave you any business.
No, yeah. So I'm going to produce a thought now. This is a historic moment where I actually produce a thought. So let me produce this thought in front of you on live TV. So let me think.
You're doing about the same. You're adding a
Yeah. No, I see your analogy. Your analogy is interesting and it's valid. So I'm trying to. So my bet is it would. Okay. Here's my claim. I will go out and say something boldly and hopefully not completely wrong. That it won't matter as much here. Let me give you the reason why. In the case of decision trees, the way you were injecting the fairness component was at every step of this greedy algorithm. Here what I'm doing I'm creating this overall global cost function and I'm minimizing it. So I have much more, no, because that's a local operation. So in the decision tree, but you're not. There is no global cost function for a decision tree. There's only the local operation. So I have my blinkers on every step. I'm saying, let me be optimal. Let me do this regularizing here. Here I have this global regularizer, and I have more flexibility to play because it's. Oh, none of these are convex. None of these things are convex.
So we may not really get, we may not really be going to be global.
No, you may not. But the point is that in some sense my argument, and this is only an opinion, is that since you're setting up the regularizer up front in the cost function, the minimizer knows ahead of time what landscape it's playing in. Whereas with the decision tree, you're only being told at every step, hey, now I'm going to give you this extra bit to compensate for. Hey, now I'm going to give you this extra bit to compensate for. You have a much more local view. But again, I could be completely wrong.
That's why, because the decision tree allows you to look.
But it's local.
If you throw it in and throw in minimizers or house it into view, they don't know. That we are able to look at things doesn't mean that these things are.
So I'm not going to say you're wrong, but I'm not going to agree with you either. So that's my conjecture, that you may not, here in this case, you are less likely to need relabeling to make it effective than in that case. In fact, in that case, I would argue that relabeling there works because, okay, this is again even fuzzier than before, right? So in the case of decision tree, there were these two approaches that said, okay, just from upfront, try to minimize the amount of information being transmitted about the sensitive attribute. So by the time you get on the leaves, you should know nothing about the attribute. It seems to me that when you do that, your relabeling will change lots of things and could cause unpleasant trade-offs in fairness and accuracy. Whereas in that case, when you said, no, let me just essentially do the classification more or less by itself, maybe with a bit of extra information about the attributes thrown in, but just do it and then relabel at the end, I have more wiggle room to play with it. And that's my vague intuition as to why that might be working. But these are things that you'd have to test out. I don't know if my intuition is correct. So here,
in this case, we have one regularizer. You can have another regularization by adding information in.
you could. But that's what you're doing, right, essentially? I mean,
That's what it's doing.
I mean, this is basically giving you, well, information loss, right? You're capturing information. Yeah. Yeah, so I don't know.
Probably what you're saying on the face of it, it may not, but however, it has to go through a testing.
Yeah. Yeah, all this is like I'm pulling random statements out of my head. I have no basis for saying anything I'm saying. But this is just my gut feeling. Yeah. So, but yeah, it's an interesting, I think these are the kinds of things where it's actually good to do some experiments to play with these notions to see, well, okay, if I try this, what will happen? If I try that, what will happen? And these are things that we haven't really done a lot of. Yeah. And again, part of that is because the code base for these things is not really fully available. It's not easy to do this, and that's, maybe we can fix that problem. So, okay. All right. So, let's take a minute to think about the ideas that are coming out of this, right? Again, like I said, we are looking at very specific models and specific ways of solving problems. But what interesting ideas have come out of this? So from the decision tree, we had this idea of, information loss or information gain. And so information between sensitive attribute or protected attribute and classifier should be low, right? There should be no information flow. And now, after going through all this, hey, wait a second, the same idea has come back again here, right? Once we see it with the right glasses on, there's the same idea showing up here and here. Right? We saw this idea of regularization that comes from here, right? Impose fairness as a regularization constraint, not a hard constraint. On the other hand, here, we looked at this as kind of a hard constraint, right? With the knapsack problem, we're saying, look, we really need to make sure our discrepancy is less than something. Do what we can to do that, right? Let's see, what other interesting ideas came out of this? The whole business of relabeling, I think, is an interesting question, but I don't really know what to make of it yet, or how to understand this in this context, or when it might be a good thing to do, when it might not. This is the discussion we just had. But you now see that we start seeing, some tools, rough tools, but some tools begin to emerge that we can maybe use as we continue on with our further exploration of these things. Okay? All right. So that's all I want to say about this third method. Like I said, I'm deliberately being a bit more vague about it because I wanted to highlight one aspect of how this works and the connection to mutual information. You will have a chance to explore these in a bit more detail. So. Any questions? Okay. Trying to decide which of two papers to talk about based on what you've seen so far. I can either start with one and then continue, or start with the other one. So, okay. All right, let me do this. The next thing we'll talk about is, well, among other things, what it allows you to deal with is SVMs. Okay? And again, a quick refresher, you've seen some of this already, but the idea of an SVM is that I like to think of it as linear separators with wiggles in them. But basically, if you want to think about SVMs, the right way to think about it is that you have some data and you want to draw a straight line between them. Right? That's basically all what's going on, right? You have linear separators. Of course, you can't always get a linear separator. If you have, the classic example that you all have seen already is this sort of two moons example. You have a bunch of data that looks like this, right? And you have a bunch of data that looks like this. And no single linear classifier is going to help you. Well, the answer to this is not to sort of make little wiggly curves. To say, well, just lift everything up to a high enough dimensional space so it looks like you can separate them with a line, and then project it down, and it'll look all wiggly. So this wiggly thing that you get from when you're running the SVM process is really a straight line, but many dimensions higher. And that's what an SVM is. It's a high dimensional straight line. At least that's how I like to think about it. Okay. Okay, so your classification task is actually very simple, right? You just have a classification problem and you want to find a straight line between them. And one important notion that will be helpful here is the idea of margin. And again, I'm going to draw this example again in the context of straight lines, but it all applies to curves, to SVMs in general. And again, I'm just piling on the reading now, right? But another beautiful area of machine learning is the whole area of SVMs and kernels and the whole theory of reproducing kernel Hilbert spaces. So it's a very rich and just very pretty area that generalizes nice flat geometries in ways that work very well. So another thing that's useful to learn. Okay. So what's margin? So I have a bunch of points here, right? These are my pluses, well, my crosses, and these are my minuses. I'm deliberately going to draw like a really easy classification task. Okay. And again, since it's an SVM, kind of a straight line, I want to draw a straight line that separates them. And of course, there are many, many straight lines you could draw here. You could draw this line, that separates them. You could draw this line, this separates them. You could draw this line, this separates them. There are lots and lots of lines. There's not one single answer. There are many good answers. But what you can do to sort of say which answers are better than other answers is to look at a notion called margin. And what that means is this. So let's say our classifier that we chose was this. Oh boy, my not very straight line here. Okay. And let's expand out sort of vertically from the margin, right? So we can, so we touch the points on either side. So we just sort of do parallel sort of moving all this. And now measure how far you got. Okay? This gap here, or maybe half the gap, depending on how you measure it. It's called the margin. So what do you think? You think margin should be big or small? What do you think is a good margin to have? What would you like? If I had two classifiers and I wrote down the margin number for both of them, one was margin number, I don't know, 5 and one was 10. Which one would you like more? Sorry? So I hear big. Do I hear small? Going once, going twice? What's the small? Everyone agrees that big is the right margin to have? Does everyone see why a big margin would be good to have?
It can easily distinguish between both classes.
Because things are further away, right?
The more the data is away from that partitioning line, the clear will be the reason which class it is going to.
So there'll be no ambiguity. You won't be like, oh, should I have put this one there? It's like it's far away, right? It's good. So large margin is kind of a good thing, right? Okay. So in fact, if you look at standard formulations of the problem of finding a linear classifier, the SVM formulation, what they basically do is try to find something that maximizes the margin. A max margin classifier is one of the standard, it's not the only one, but it's one of the standard ways in which you write down the problem of finding the best separator for these things. Okay, so large margin is good. But large margin is also good in another sense, because there are these results in the theory of machine learning that talk about something called a generalization bound, right? Let me see how I say this. So, how many of you have heard of a generalization bound in machine learning? Anyone? Have you heard the term at all? Not a little bit, okay. A couple of you, yeah. So we build a model, we train on data, and we run on test data, and we say, okay, it looks good. And we're happy. Why are we happy? It just ran on the data, right? What's so special? Tomorrow someone will come with a different decision, our model will break. But we don't believe that will happen. We actually believe that when we train the model on the data, that the model actually captures some deeper truth that will remain true even if we get a new data set tomorrow. Why do we believe that? What reason do we have to believe that the model we built on today's data will be the right model when you get data tomorrow? And it's a founding assumption in machine learning, right? We don't even talk about this, it's just there all the time. Well, we do talk about it, but if you haven't thought about this, think about this. Why is it okay?
We actually assume that it covers all the permutation of all those values which can be there, and it has gone every bit of information which is required further.
You assume the data set has all the information that you're likely to see in the future. That's what you're saying. You believe this, right? So the belief is that when you build your model from your training data, right, that the properties of the model you get apply to all the data you will see in the future. Effectively, you assume that your trained data is drawn from some underlying distribution, right? So the way you think about machine learning is not that you got a bunch of data and you did something. You typically think that, okay, there is some process in the world that's spitting out data, right? And it'll keep spitting out data forever. Your job is to take what are hopefully uniform samples from this and build a model. So you take this and you build a model. And the hope is that because you've taken a uniform sample from this, that your data is somehow representative of the population for the task you care about. And so when you build a model on this, it'll be representative. Okay, that's great. Can I build my model on one data point? Probably not. Can I use two? I don't know, maybe 3, 4, 1,000, 1,000,000, 1,000,000,000? How much do I need to be sure that I've got a decent answer? The answer to that question is what this is. Generalization bounds in machine learning tell you how many samples you need from the underlying data distribution so that when you build your model, its results generalize to the overall sample. That's where the word comes from, right? So it's a very important thing. And again, this, if you take a course on the theory on machine learning, these are the kinds of things you talk about a lot. Because you say, okay, how many samples do I actually need to be sure? And so there's always a trade-off. So you'll say, okay, so basically you'll say something like, there is certain amount of, okay, so I say I get my model on my data has certain amount of error, right? What will my model look like on my actual, well, on the population at large? What I want to say is that the error I get on the data, epsilon, is very close to the error I get on the true population, right? So I want to measure somehow the error on the data and the error on the population. And what I want to say is that this error is controlled by some function of n and other parameters of the and typically it's a decreasing function. As n increases, this gap decreases. The more samples I take, the more I'm confident that whatever bounds I get reflect what's going to be seen in the general population. Okay, why did I go on this long digression about generalization bounds? Well, because they're awesome, but that's the other reason. And then the real reason I went on this digression to generalization bounds is because you can relate generalization bounds for SVMs to the margin. That effectively, the bigger the margin, right, the more easily classifiable the data is, the fewer the samples you need to get a good answer. And this kind of makes intuitive sense, right? If the data points are really far apart, and I take a few samples of it, I mean, if they're so far apart, then even a few samples, I'm going to get a pretty good answer. But if they're close, then I might need to work very hard to get a good bound on my error, right? Because here's what could happen. Suppose I have points here, and I have points here. So there is a separator, but the margin is very small. Now, if I pick a sample, I might pick, oh, I pick this point, I pick this point, I pick this point, I pick this point, right? And now I run my classifier on these 4 points, which will look like this, this. I just broke it. Huh? I just repaired it. There are many classifiers I could build on this. As far as I'm concerned, you know, this could be a classifier, this could be a classifier. But if you take this classifier and put it back on this data, you'll get a huge error. This will not generalize well. But if I got enough samples to really figure out the contour of this boundary, then you can see, okay, I'm going to do a lot better. So this makes intuitive sense, that the larger the margin, the fewer the number of samples I need to get a good answer to my classification problem. You can actually formally relate this. The formal expression basically says that the difference in these two errors roughly goes as 1 over theta squared, where theta is the margin. So as the margin gets bigger, the difference in these two gets smaller for a fixed number of samples, right? So there are lots of other parameters that I won't get into. Okay.
Are there any methods for getting this generalization bound for normal backpropagation that are got?
Backpropagation is very hard. Any kind of theoretical analysis of neural networks is very, very hard. Most of the work on generalization bounds has been for these more controlled settings here. And there is a lot of work. And again, I'm not by any means an expert on this topic, but there's some wonderful books you can read on this thing. Neural networks are tricky. Yeah. But it's an important question to ask, right? For all these reasons. So how do we know how many samples we need to have a reliable answer?
It's the most important thing.
It's exactly, because how do you know when to stop, right? I mean, yeah, exactly. Okay. So, as has been happening a lot today, I've gone a couple of detours. I'm trying to sort of reel myself back in, right? So we started with SVMs. I promised I wanted to talk about how to do fairness-aware SVMs. I introduced the idea of margin. I explained, hopefully, why margin is important, because margin controls the degree to which you can be confident about your answer. This is going to be important because the way we're going to play with fairness is going to be by playing with the margin. And that's why I want to talk about that. Okay? So let me give you the idea in the paper. So let's assume that we have some kind of classifier, binary classifier, and we'll write it in the following form. That h of x is equal to the sine of some confidence function. Okay? In other words, think of the confidence function as some measure, let's say, I don't know, of distance to the decision boundary. Right? You can think of, for example, one way to think about this is that there's some kind of sigmoid function that says that confidence function is some kind of sigmoid, some kind of, I don't know, 2 sigmoid theta transpose x minus 1, which will basically scale your sigmoid to be between -1 and +1 or something like that, right? Or something else. It's some function that basically measures your confidence or your distance from the boundary. So the further you are away on one side, and this is also a signed function. So it's plus on one side and minus on the other side. And so the sign just says, okay, I don't care what the value is, just look at the direction, and that gives the direction. So let's say you have some kind of classifier like this, right? For example, for SVMs, the way this works is that this function here will be something like, in the case of a linear classifier, it'll be W transpose X plus some bias term, right? And if it's an SVM, it's really more like W transpose phi of X, where phi is the lifted map in the feature space plus B, right? This is some number, okay? So there's some kind of function, and you take the sign, and the sign tells you things. So this captures, among other things, SVMs, also logistic regression and other things like that. So it's a more general framework. So now the decision boundary for this classifier is 0, right? So the way we set this up, you're going to be 0 is the decision boundary because one side of 0 you'll get one label, one side, other side of 0 you get the other label. Okay. But let's define a shifted boundary. So we'll call a shifted boundary lambda. Okay. So we'll get a modified classifier which looks like this. So instead of being this before, it'll be two different things. It'll be well, actually, okay. So let's fix a set and fix a set subset of X so that this is 1 if it's shifted and X belongs to S. Okay, so for some subset of the population, we will do this, and it's the original value otherwise. Okay? What is this doing? For now, let's pretend that this is not there, or let's pretend that S is equal to X. Let's not worry about this. Let's just look at what this is doing. So we had our original classification boundary here. With this thing here. Right? So we had the boundary here and we had the margin either side. Right? So this was, yeah, okay. Well, let me just draw it on the line. It'll be a bit, forget the classification right now, just look at the line. So we have a line here, and we have 0, and we're basically saying, okay, on one side or the other, you're just going to use 0. So let's say our confidence function, hold on a second. Yeah, okay. let me draw this again. So the value of x doesn't really, so x is whatever it is, right? But the confidence function is doing something, and at some point it, it dips and it goes below 0, right? And this is what it looks like. So everything here, you'll have h of x is equal to -1, everything here, h of x is equal to +1, right? Once it cuts below. Okay. What's going to happen here? If you now draw h lambda of x, so let's put on the, this is the minus lambda mark here, right? What we're saying is that instead of putting a boundary here, where all of this is +1, all of this is -1, what's going to happen? We're going to shift this boundary down. So now things here we've essentially moved the decision boundary away. One way to think about that in the case of a hyperplane is that we've kind of moved the hyperplane over, we slid it over to one side, we've changed the margin a little bit. Okay? And this can be done for any lambda. And now if we add back in the constraint that, x must belong to the subset, we're saying, okay, do the shifting, but only for some items, not for all the items. Okay, why would we do this? The idea is to, remember, we were trying to build a classifier for SVMs, and we wanted to make it fairness aware. Right? So the idea of this is somehow to build your model is to build a modified sort of model here that uses lambda as a knob to control the amount of fairness you want to achieve in addition to getting what you have. And so if you remember from, I think, 2 days ago, we talked about this approach to modifying the labels of the input to get the desired outcome. We had this discussion about whether that's okay to do, but what we said was, okay, we'll just change the labels, and we said, let's look at the labels kind of near the boundary and change them around to balance out what we're doing. Okay? I want you to remember that, because what we're essentially doing here is saying, we're not going to change the labels on the inputs, we're going to shift our boundary a bit. Because what's going to happen is that, if you think of this case here, if you had a classifier here, of course here if you move it, nothing will happen, right? But if you have this classifier here and you move it a little bit, you're going to start changing the labels of some points effectively. We're not changing the labels of the input, but we're changing what the classifier does to them. And yes, you might pay some price and accuracy, but okay, whatever. And why would you do that? You would do that because you want to maintain this statistical discrepancy. By doing this movement, you will change, so you can compute the initial classifier once again, and you can say, what is the discrepancy score for this classifier? So the procedure here would look something like, find H, your original classifier, and compute the statistical discrepancy. And then you would say, pick a lambda such that H of lambda has statistical discrepancy less than some threshold, our usual threshold for statistical discrepancy. Okay? And find the minimal error such. So again, the idea here is try to take your classifier boundary and move it a little bit to adjust for your concerns over bias. Okay? And what you get from that? What you get from that is that now you can achieve the discrepancy you want, but you get one more thing. What you get is a formal guarantee. So what you can show that using the same theory we showed, that how to relate generalization bounds to error in terms of margin, what we're doing here essentially is playing with the margin. We're reducing the margin in some ways to do this, right? And so what you can prove, and what they prove in this paper, is that you can give a formal relationship between the fairness you achieve and the amount of accuracy you lose in this case. and how good your generalization bounds are. So the one thing that I think is interesting about this paper that the authors point out, this is kind of a nice feature that one of the things we've always struggled with in all this discussion is, well, how do you balance accuracy and fairness, right? How do you decide what to do? And this is one attempt that they have to try and give a formal relationship between these notions here by using the idea of the theory of margins to help.
How can we say that like we are introducing bias or we are removing bias?
Well, their argument is that you're trying to remove bias by reducing the statistical discrepancy. Right? You remove the problem of fairness by reducing the statistical discrepancy. You will lose accuracy, but you will lose as little of it as possible, and you can prove some bounds about how good this will be in the limit, in the generalization. Does that answer your question? I'm not sure it does.
Like there is a boundary.
Yeah.
We have got to use this algorithm.
Yeah.
And then we are shifting this boundary.
Yeah.
But we are getting some errors for some points.
Yeah.
So we are not sure that if the data is correct, suppose, and because of shifting this, the value will be changed.
Not the data, but the output. Yeah.
But the output will change.
Yeah.
But we know that the output was correct.
No, but the output is just what the classifier gives you, right? I mean, there's no previous output. This is what the class. So the classifier has some error, right? So yeah, if you reran the classifier on your training data, it might give some errors, but it was going to give some errors anyway, right? I mean, we're not fiddling with the data. You're just saying, can I build a different classifier that'll have errors in different ways? So one of the things we talked about, right, last time was this idea of error profiles. That you will make errors, but can you make your errors more balanced? Maybe one way to argue this is that, okay, you're going to make errors anyway, and you might make more, but maybe you spread them out better. You're not making systematic errors in any one particular group. But that's not what they're saying, but you could interpret this in that light. Anyway, I think we're about time. It's 1 o'clock. This might be time to adjourn for now. And we'll reconvene at 3 o'clock with more of the same. So, yeah.
3 o'clock we have a class,
Yeah.
and tomorrow we'll have that.
Yes. Well, we'll have a bit of food. You've had some coffee, and are ready to get back into things. So let's go back to our big chart from the morning, right? So we said we want to look at models and kind of right. So we said we're going to look at different ways in which you can build classifiers based on this, or build models that have certain kinds of fairness measures. So we had decision trees. We looked at naive Bayes briefly. We very quickly went and talked about logistic regression. And then we finally looked at SVMs, but of course this applies to logistic regression as well. Anything where you have some kind of decision boundary would work as well. And in all cases, let's see, so here we looked at statistical discrepancy. Same thing here. Here we looked at a notion more of sort of a mutual information between the classified attribute and the sensitive attribute. And then here finally we looked again at statistical discrepancy. Okay? So far we've seen a lot of looking at statistical discrepancy, and in the things I'm going to talk about today, this section, the 3 methods I'm going to discuss, all 3 of them look at trying to model fairness, trying to capture fairness in a different definition of fairness. So none of these. Okay? And so the first one we're going to look at is an interesting technique where there isn't a specific model that's being used as such that I can write down here. And what's being used here is kind of a combination of statistical discrepancy and individual fairness. Okay? And the technique being used here is actually very interesting. It's a very different way of thinking about the problem, but even then it has some similarities to things we've seen before. Okay? So let me But before I do that, are there any questions on any of the things we've seen thus far in the morning? All these methods, these approaches? You kind of, begin to get a sense of a vague sense of how they're operating, and hopefully at this point there will be no further surprises, right? When I come up with a new method, you should be able to say, oh yeah, I kind of see what they're doing because we've already seen these kinds of ideas being used before. Okay? All right, good. So let's get into it then. So this paper, even the title tells you that something different is going on here. And the title of the paper is Learning Fair Representations. So I'm just going to put that here because it doesn't really fit into this whole what is your model framework as the other ones. Okay? And I want to emphasize the word representations in this. Because it's in some sense what this paper is doing. And we will see another example of this right at the end of the course. Is it's not trying to build a classifier for data or directly and try to modify the cost function or do something with the classifier. It's actually trying to change the space the data lives in. Okay, so this is in some ways similar to the whole, oh, let's modify the input idea, but it's different because it's changing the entire space itself. And so one potential advantage of a method like this is that if you have new data that comes in, you might be able to classify that new data in an effective way because there's a mapping. What it does is create a mapping to a brand new space. You just take your data, map it to the new space, and then run your classifier there. So let me say more about that. But that's what makes it both different and interesting compared to the methods we've seen so far. And at a high level, right, what this method is trying to do is something like this. So we think of our data, let's call it X, and there's some kind of classifier we want to build on it, right? And we are worried in these situations about issues of bias, that maybe the classifier is doing something, it's messing up with the data, it's giving bad answers. And then all these methods say, okay, do something with the classifier to fix your problem. All methods from yesterday said do something with the data to fix your problem. But what this approach says is that we'll separate the concerns into two parts. There are two concerns, right? The concern is, I want to classify. And the second concern is, I want to be fair. Right? And in all of today's discussion, we've been trying to combine these two things together to do fair classification. But this paper says, suppose we can actually separate out these two ideas, right? And in the following manner, that instead of this picture with data and a model, we'll take our data and we'll come up with some new data. Okay? And our model is not allowed to be run on the data. It has to be run on this modified data. And so the goal is to prepare the data in such a way that it's unbiased, and then do the classification in such a way that it's accurate. Okay? And if somehow I can do this, then it's a cleaner way of thinking about the problem because I've separated out these two principles that I want to explore. Okay? Now, of course, these two things are somewhat related, right? If I just did one and not the other, then there might be influence effects from here, this process of transformation, that might affect my efficacy of my classifier, how good it is. And so in actual fact, what they're going to do is train a model, but simultaneously train a representation. Now, if any of you have done anything with deep learning, right? How many of you ever played around with neural nets in any form or the other, in some ways? Just you? Anyone else? Anyone use TensorFlow or played with TensorFlow? There's lots of nice tools out there to play with sort of simple deep learning ideas. And I mean, in brief, right, a neural network is this gigantic network of nodes. Nodes have feedback and they put things in each other. But what's interesting about neural networks is that when you train a neural network, what you're actually getting at the end is really some kind of new representation of the data. And then you have a classification layer built on top of that. So in some sense, this is doing something with a similar spirit. It's trying to change the representation of the data so that the task you're trying to perform becomes a lot easier, or becomes a lot more effective, or becomes whatever you want it to be. Okay? And so this notion, again, is a very general notion in machine learning of if you want to classify things, change the representation so then this task becomes easier to do. And sometimes you might do these things at the same time. That the classification itself will guide the representation, and the representation will guide the classification, and so on and so on and so on. So there's this whole area of kernel learning, for example, where you try to learn the right kernel for your SVM. There's this area of distance metric learning, where you learn the right distance metric to do clustering on your data. There's a whole bunch of things out there which are quite interesting. And they all have the same philosophical principle, that you can change the way your data looks to make your task look easier. Okay. So having said that, the relevant question is how you do all these things, right? So we're going to set up some things, and we'll sort of set up the whole process of how to do this, and we'll explain how this works. Okay. So remember, the goal is to not just build a classifier that's fair and accurate, but it's to actually get a new representation of the data. So that, for example, if a new point comes in, this mapping, which I get from here, can be used to map the new point to something here, and that'll be there. So what are these things going to be? So as usual, we have some, we have some data set, and we have some, it has some attributes. It has one sensitive attribute that you're worried about, race or gender or whatever it is. And you have, as usual, your training set and all the other things that you have. Okay. The key idea, the way we're going to encode this representation, is in two parts. What we're going to say is that we're going to fix some parameter k, okay, and essentially cluster the data. We're going to create clusters, so this variable z will take values in the range 1 to k, right? And so for each input point, there'll be a corresponding zi, which will tell me which cluster label it's in, okay? So there'll be a bunch of clusters, k of them. And with each cluster will be associated some vector. So there's some vector v1, v2, up to vk. If you're familiar with clustering, you can think of this as the cluster, and this is the cluster center. But I'm not specifically saying it's a clustering problem. Okay? All right. The idea is that we will take our input points x and somehow map them to different clusters. Okay? And the classifier is only allowed to look at the clusters when clustering. So the classifier bases its decision on which clusters you're members of, not based on who you are. Okay? So that's how we want to decouple the process of making the data unbiased and the process of classification. That somehow the classifier is only allowed to look at this, and this part is what transforms the data to the point z. Okay? And if somehow we can do this, then we'll have done a good job in building a fair and accurate classifier. So the question now is, what properties do we need of this process? Okay, so we'll assume certain things to make the process reasonable. And what we will ask for is this. Let me first talk about how we'll encode fairness in this representation. So when I talk about fairness now, I'm only going to talk about this mapping here. I'm actually not going to talk about what happens there. So what will it mean to be fair in this context? It means that if you look at all the points that are mapped to any particular cluster, right? Or if you look at, for a given point, which clusters it might be mapped to. So assume there's some kind of probabilistic mapping. So for each point x, there's some probability that z is equal to k given x. Or z is equal to some j, let's say, given x. So for each j, there's some probability associated with this point. Let's say that there are two sets. There is the there's a set of points x plus, which is all x for which the sensitive attribute S is equal to 1. So this is the protected group. And then there's X minus, which is the rest of it. Okay? What would we want from these assignment probabilities in order to ensure statistical fairness, some kind of parity? What would we like to see? What would we, or rather, what would be an effective way of putting things? Now, think of everything we've talked about so far, right? So, what would we like about this representation in terms of fairness? How would we want to make it be?
Like we were doing in the earlier cases, whether it is there, it is not there, is not effectively probability.
Sorry, can you repeat that?
We have written that formula PR, some x given g is equal to 0 and g is not 0.
It should be more or less the same. Right. So what we'd like to say is that something like for each j, right, the probability that z is equal to j given x that belongs to x plus, right, should be more or less the same as the probability of z belonging to j for x belonging to x minus. In other words, the likelihood of being assigned to a cluster should not really depend on which group you're in. It should be more or less the same, right? So it's not going to be like, well, this group has mostly members from X plus and this group has mostly members from X minus. That would violate this constraint. So each of these groups will be kind of confused in the same way. They'll have roughly the same amount of things from these different groups, right? And if you think about that, this is the same idea we've been seeing all along, right? That like even the decision tree model, you want to sort of confuse the decision tree. You want to make sure you can't really distinguish things, that are coming out of it. So you do that here. So this is the criteria we want, okay? We will also assume that there is some relationship between the V and the probabilities, right? So a standard way to do this is to use what is called a softmax. So what we want to say is that somehow we want these VIs to be informative. We want them to accurately capture the actual points in the space. So if you think of my cluster, if this is a cluster, if I have a bunch of points in the space, I would like my V to be somewhere in the middle between them. And more generally, if I have a bunch of clusters and I have a point, I would expect that this point is more likely to be associated with this cluster and less likely to be associated with those clusters because it's closer inside, right? So I have some notion of distance, let's say. So once you have some notion of distance, let's say it's a normal Euclidean distance in the space, right? Then I can connect up these two independent, so far independent parameters, the V's and the Z's. I can say that what I want is that the probability of Z equal to J given X, for any X, should relate somehow to the distance of X from the different things. So one way to do this is say, okay, assign it a higher probability if it's closer, and that's an easy thing to do. You just take the average of all the distances and then normalize it. A slightly better way is what's called a softmax. So this is basically, this is going to be, let me see if I make sure I get this right. So it'll be e to the minus distance of x to vj divided by the sum of all the distances. So what is this funny expression? This is called a softmax. Again, this shows up a lot in deep learning. But what it does is, intuitively think of it this way, right? What this is doing is this number, what happens to it? If d is large, this number gets small. So the relative fraction, the likelihood, forget this number for now. The relative likelihood of assigning a point to a cluster is inversely related exponentially to its distance from that cluster. That's kind of what we expect, right? The reason why you do this exponential thing is to make that effect even more strong. And it's called a softmax because if you put a parameter lambda here and you send lambda to infinity, then effectively this will just give you the closest. In the limit, you'll just get the closest neighbor. So this is kind of a smooth nearest neighbor. Think of it that way. So softmax. Okay? Right. We won't have that here anymore. So think of this just like, a max. All kind of the closest point, but you want to assign some small likelihood of assigned other thing. So the probability of being assigned here is very small, but it's not 0. There's at least some chance you might assign it there. Okay, so this gives you some. All right. So what we've done now is that we've introduced a new representation of the data. We've introduced 2 parameters, the probability of assigning a point to a cluster and also the cluster representative. And we've linked those 2 parameters in this way. So they're not independent of each other. Okay. All right. So what do we want now from this whole process? What are the criteria we need? And remember when I was telling you about logistic regression, I said that a common trick in machine learning is to write down some gigantic cost function, throw in all the terms you want, and then minimize the whole thing altogether, just to balance out these things. We're going to do that right now. We're going to write down a whole bunch of things we want. We're going to write down one cost function for each of them, and then we're just going to balance them all together. Okay? So what are the things I would like to have? So the first thing I'd like to have is some notion of parity, which I've already written down out here. So I want that my representation Z has statistical parity. Okay? What else do I want from this whole process? The other thing I want is that I have a good classification. So I want, and I haven't yet told you what the classification is going to look like. Okay? So I want parity and I want good classification. But I also want one more thing. This is saying something about this is saying something about that, but I'm not going to get that unless something else happens here. I mean, if this is just, has statistical parity, I can make up any kind of representation and somehow guarantee that. How am I going to make sure that I have an accurate classification? How do I have any hope of doing this? The third thing you want is somehow that the new representation of a point kind of looks like the old representation. In other words, I want my points to be changed to maintain parity. I don't want to change them too much. I want to be careful about how much I change them. And I want all of this to be focused eventually on getting good classification. Okay? So we want to achieve all of these goals. And so the question is how we're going to do it. Okay. Any questions so far?
The new representation of a point is equal to old representation.
Almost, roughly the same.
So we are talking about X or we are talking about Z?
So what I'm going to describe, I've said that I assign a point to different clusters. This is going to give me a new representation of X, and I haven't written that down yet. When I construct that new representation, which is going to be a function of Z and also the V's, then I will want that new representation is more or less like the old one. Yeah. Okay.
Because this is important property.
Yes, exactly. It's a very important property. Otherwise, you have no control over what's going on. Yeah. Yeah.
Why it's not in the part where it's modifying the information?
It is and it isn't. In the sense of you are modifying the input, but you're also training a classifier at the same time.
Okay.
So there's this whole, okay, you modify the input, I will modify the classifier. This paper is saying, no, let's do it all together. That's the difference. So I mean, okay, no taxonomization of techniques is perfect. But in the sense, this is kind of sitting in the middle somewhere. It is really building a new classifier. But at the same time, it's as a byproduct, it's getting a new representation as well. So it's doing both things. And it's not actually, so this is a bit, I guess this is a, yeah, okay, I don't want to say what I was going to say, because I don't think that's correct. So. Okay. All right. So how are we going to set up this whole process? Remember, our goal now is to set up some gigantic cost function that we will minimize as a function of the parameters we're searching for. And that cost function has to have 3 parts to it. And then we'll add them all up, put some lambdas, and cross-validate till the cows come home, and then we'll be on. Okay. What should I erase? Give me a second. So, as they say, let's start at the beginning. So, let's introduce some notation just to make life a bit simple. We will define so in other words, this is just a shorthand way of saying, okay, just tell me the particular probability of a point being assigned to a particular prototype or cluster in this thing. That's all. There's nothing going on here. I just want to don't have to keep writing it all over again. So I just put this. So it'll be a bit easier to look at. Okay. So now we want to encode the first criterion, which is this criterion. Of course, now this criterion is easy to express. We can now define let's call this. What this is going to represent is the this overall probability. So this is going to be summed over essentially so in other words, MNK was the probability of a particular point being assigned to cluster K. Let's ask ourselves, what's the probability that some point in the protected set gets assigned to K? Okay? Or rather, this is the expected value of that quantity. So in other words, this is really the expected value of the probability that z is equal to k, given that x belongs to x plus. Right? So this is the sample mean basically of that quantity. And similarly, you can do the same thing for m minus. Right? In the same way, you just sum over x minus. In which case now, can we say something directly about what this first condition is? Can we express this first condition mathematically in this setting? So, any thoughts on that? Sorry?
The difference between NK plus and NK minus is small.
Right. We want this is small. Why? Because mk plus is the expected value of the probability of being assigned to a cluster K if you are in the protected set, right? Which is this quantity right here. Mk minus is the same thing if you're not in a protected set, which is this quantity here. Statistical parity says we should have no difference in what we see here based on which group you're in, and so we want to encode these two things there. Okay? And so just one way of saying this is small. And of course, we want to write this as a cost function to minimize. So the first cost function, call this L1, is going to be the sum of okay? I used K, but I shouldn't have used K. So this is the first number that if we make this number small, we will be happy with our properties here. Okay? All right. Now, the next thing we'll do is is ask about, this is part 1. So let's actually look at L3 next, because that's our next in the pipeline. And to do L3, we're basically saying, okay, we have some new representation of a point, and we want it to be the same as the old representation, which is X itself. Well, what is the new representation of point? Well, what I'm saying is this. Imagine this. I have a point. I'm assigning it to one of these clusters with a certain probability, right? Each cluster has a particular vector associated with it. What is the expected thing I look like? Well, if I assign here, I look like this. If I'm assigned here, I look like that. So my expected lookalike will be right? Because with this probability, I'm assigned to the cluster that looks like this. And so if I want to find its expected, what it expectedly looks like, it will be this. This is my new representation. So if this is my new representation, what I want is that the new representation should look like the old representation. And since we're using L2 distance, I'm saying they're not. I'm asserting that I'm going to model the problem as them not being in different spaces. I'm saying my VK lie in the same space as the X's. You could, of course, say, well, what happens if you're in a completely different space? That's a perfectly valid point. You'd have to define this differently. Yeah, so there's a one-to-one map. Every point gets a new representative, yeah. Okay? And so again, we can quantify this, and since we're doing L2, it's convenient to square it, so we don't have square roots. So the L2 function is the sum over all j equal to 1 to n right, so I'm squaring it just to make life simple. So that's my second cost. So now I'll actually call it L3, not L2. So I've got now this, and I've now got this. What's left is to get this. Okay? So now we have to actually come up with a prediction. So we're going to assume we're doing some kind of linear classification, right? And so we have some kind of, remember, the goal of our representation is to limit our classifier to working only with these representations, okay? Which means all the classifier is allowed to do is use this information to build a classifier, okay? So, so think of this classifier that we're building as having some prediction for this, some prediction for this, some prediction for this, and some prediction for that, right? Based on what it is. So it's a binary classification or 0, 1, 0, 1, or whatever. Okay? So we'll encode the predictions the classifier makes on these entities by some number wi. So in other words, the classifier, it takes in a vi and outputs a prediction wi. Okay? That's all it's allowed to do. It's not allowed to look at the data. So it has to just look at the representatives. So the classifier can be described by a collection of wi. Okay? And so now if you say, okay, well, we took a point, with some probability we assigned it to one of these, what is the classification outcome going to be? Well, if we assign it to this, then W1 will be the classification outcome. If we assign it to this, then W2 will be the classification outcome. Well, we know what those probabilities are. So we can say the resulting value, let's call this yi hat, predicted by the algorithm for this point is going to look like the sum of from j equal to 1 to k, the weight, the actual predictor that you have, times the probability you were assigned to that predictor, which is basically Mij. No, yeah, Mij. Okay, again, note, this I is the point, and we're asking for this point, which predictor is it assigned to? Then use the weight for that predictor, take the average over all predictors. So they all vote. So we're assuming some kind of linear combination of these things. And what do we want? We want that this predictor matches what the ground truth is, because it's a supervised classification problem. So you can write out whatever error metric you want. In this paper, they use a sort of a binary entropy. You could imagine running, you could say, okay, sum of yi minus yi squared. They happen to use basically a log version of this. So this is minus yi log yi hat minus 1 minus yi log 1 minus yi hat. Again, you can take your pick. I don't think there's any particular reason to choose one versus the other, but some kind of measure of discrepancy. This is an entropic measure of discrepancy, this is an L2 measure of discrepancy, and we'll call whatever we pick here to be L3. Oh, L2, sorry. Okay? Sorry, I changed my guy, because I wanted to keep them in the same order we did them here, so that's why. Yeah. Okay? There are various customizations you can do if you want to be really fancy, and the paper discusses some of these more customizations, but they don't fundamentally change the basic idea, so I'm not going to worry about them. But ultimately, what we get, our huge objective function now that we want to minimize, is going to be L is equal to and you want to minimize this quantity. And again, because these lambda parameters are unknown balancing parameters, in practice you would use some kind of cross-validation to find the right values for these things. Okay. So what are the unknowns here? So by the way, K, so there are a couple of things that are fixed ahead of time and we don't know what they are. So like K is a fixed parameter, which you can also cross-validate for. It's like in clustering, you choose K or you fix K in some way. This is a doing clustering. But what are the unknowns here? The unknown parameters here are the VK, right, which are your representations of your clusters, and the WK, which are the predictions for the representatives, right? So again, pick the representation and pick the classifier for the representation. Everything else can be derived from that. The Z's can be derived from this, which means you have the M's, which means you can do everything else you want. So these are ultimately the variables you have to worry about. Right? So you have this, and this is your, again, this is how a lot of machine learning works. You have this gigantic minimization, which is a function of these variables. You do gradient descent, you do other things, you do what have you to try and solve this. And so what you get at the end of this, if you've done the whole minimization and you get the answer, you now get, again, representations. The representations through this model give you assignments for points. And if a new point comes along and you have this, all you have to do is plug it into this to say, okay, for this new point, what is the probability of assigning it to any of these clusters? Well, that tells you exactly what it needs to be. So this works even for new data, out of sample data. And the WKs tell you what the answers are going to be. So in this process, you've combined both the idea of classifying as well as maintaining statistical parity. Now, the paper makes the argument, which is a little less clear to me, that this captures both statistical parity and individual fairness. It obviously tries to capture statistical parity, but how it captures individual fairness is a little bit trickier. The way in which they argue that it does capture individual fairness is by arguing that the representation is good. Because if the representation is good, then you're hopefully going to make, when you're going to make your decisions, if 2 points are similar, you are likely to make the same decision for both of them. Why? Because if 2 points are very similar to each other, then they're close. If they're close, they have roughly the same assignment of probabilities to the cluster centers. If they are the same assignment of probabilities to the cluster centers, they will have roughly the same classification value. Right? And these can all be calculated out. So that's the argument by which they claim to be able to capture both statistical parity, which is explicit, and individual fairness, which is a bit more implicit. Maybe that last bit went a bit quickly. Any questions? When I say any questions, it really means I want to drink some water. So. What I'm saying is that I now have competing objectives, all of these, right? And I'm trying to do a multi-objective minimization there. And clearly the values of the lambda parameters will weight these objectives differently. If I really, really cared about parity and I didn't care about the others, I could artificially make lambda 1 very large. So then my optimization would pay much more attention to lambda 1 and would pay less attention to the others. Or I could say, no, I don't want to make a decision up front. My data might drive this decision for me. So I'll just do the optimization and try it with different values of lambda and choose the best combination. And that combination will reveal what seems to work best to my data when I want to balance these criteria. So in some sense, it's being fair, right? I mean, in some of the previous methods, you said, well, why are you making it so important to be unbiased? What about accuracy? This is saying, look, we want to do all these things, and we have to balance them somehow.
You have to define the preference.
Yeah. Or you have to at least, say, look, either you say, I'm going to put my thumb on the scale and decide which is more important, or I'll let the system figure it out from the data. But all these terms are there and can be seen and can be controlled.
So we are having some size of x, then we are representing it in form of z. Now suppose
in the form of x hat. And x, yeah, x bar.
So suppose if x is having some parameter which is sensitive,
Yeah.
so whether it will be a good idea to remove it into the new representation, because if it is again there in the new representation x hat, so ultimately it is there in some other.
Right, so the way in which you hope that it's not there is by enforcing this.
Yeah. So it means we can also eliminate this into the new representation.
That's the hope. Yeah, that's exactly the hope here. By encouraging the optimizer to reduce this number, you are helping it do that. But you're not telling it that's the most important thing to do. You're saying, look, do that, and do this, and stand on one leg and juggle 3 balls all the same time. And you have to hope that it does it. That's why, you have this big optimizer, you just plug it in and cross your fingers and hope for the best. This is modern machine learning. So. Using loss functions to guide the navigation. No, yeah. Well, I'm not telling you yet. All I'm saying is that you just throw into some big optimization scheme, gradient descent or stochastic gradient descent, and that'll produce these answers for you.
You get no guarantee that there is no discrete impact.
You can't get guarantees, not unless you drive these things really high. Yeah, you're not even trying to. You're trying to balance these criteria. You had a question? So this is a one-time training process. So you run the whole training procedure. The output of the training procedure are these. These define your new representation, and now you're done. If a new point comes in, you have a couple of choices. You can say, oh my God, this new data looks totally different, I need to rebuild my model. Or you can say, no, I'll use this with the current model. And you can because of this. So for example, when you do dimensionality reduction, right, you do something like PCA, you get a new representation for the data, but that only works for that data. If a new point comes in, it won't work anymore, right? It doesn't work on the fly. So it's nice to have a system where you can sort of update it as, not update it, but use it even as new points come in, and that's what this is trying to do.
But if this part is fair, like we are using initially the sensitive parameter, but later on when we are creating our classifier, we are eliminating.
Right, so the idea is that we don't want the classifier to have to bother itself with issues of fairness. We want to modify the data to just let it do what it wants. So we're modifying the data. But but the classifier, the modification of the data should also be influenced by the accuracy of the outcome. And so that's why there's this tension. Right, so there's this tension between these goals here that this method is combining. by not doing just one or just the other, by doing both at the same time, it's trying to allow the methods to talk to each other. Like the good classification method and the good representation method to talk to each other.
If we increase the value of lambda, like lambda 1 to infinity,
Yes.
then this method reduces to the one we have talked about in last class.
Yes. Yes. It'll just be a statistical parity ensuring technique. But it'll be even worse in some sense because you will not care about accuracy at all. I mean, it would be okay to just create complete garbage. It would allow that. Now, if you set lambda 1 to infinity and lambda 2 to infinity, or just set lambda 3 to 0, then it becomes a little bit more interesting. Okay, then you're getting something that kind of, it's a sort of a good approximation of the original data.
So, can we get such data sets which are having these already known sensitive parameters?
Yes, so there's a couple of 3 or 4 standard data sets that everyone uses in all these papers. There's one called, and I can point, and that's one thing I want to do for the labs is to have you play with them. There's one data set, it's a census data set. It's called adult. It has things like income level and age and gender and race and things like that from the US Census Bureau. There's another data set called a German credit data set, which is decisions about credit decisions made, and there is some known gender bias in that data. And so these are data sets that all these papers use and we've used, and this is what I want to give to you all to play with for some of the lab work. So you can sort of play your own thing and see. Yeah. Okay. Other questions? It'll do something interesting. It won't do complete garbage.
If you put lambda 0 and lambda 3 as infinity, lambda 1 and lambda 3, that means like the data is.
Wait, what are you putting to 0? Wait, what are you doing?
So like put lambda 2 as 0.
Yeah.
A good classification parameter.
Okay.
And lambda 1 and lambda 3 as infinity. That means that.
Yeah, so that might, I don't know what that would do. The problem is this. In this particular framework, the classifier only gets to see the representatives, nothing else. It's not looking at the original data.
Yeah.
So now if you set lambda 2 to 0, you're saying, well, I can make up any old stuff in how my data looks. I think what will happen there is that you will lose the individual fairness promise that this is giving you. Because what will happen is that 2 points that were very close might end up mapping very far because there's no L2 to hold them back, and then your decision will be very different, and so it could be very bad. So keeping lambda 2 non-zero tries to ensure individual fairness, that 2 individuals who are close should be treated the same. Okay? So this is the statistical discrepancy, this is the individual fairness, and this is the accuracy. Think of it that way. That's what each of them are doing for you. And that is the promise of the paper, that it tries to balance out all these concerns. Good. More questions? Okay, all right. So then now we'll move on to another paper that still stays within the realm of classification, but uses a different fairness notion, the one that we have not seen in this discussion today yet. I mean, I mentioned it, but we haven't seen it yet. This is this whole equalizing odds idea. Okay, I'm going to start wrapping this up. Okay. So the next example we're going to look at. So maybe we should, so what if we, maybe it's good to stop and reflect on what we may have learned more generally about this whole topic for today from this particular method, right? So we learned some things from all the methods from earlier. The idea of matching statistical parity, that's sort of not new. We've seen that idea before. I think the idea of creating, what I think one takeaway from this paper that's different is this idea of creating a new representation of the data. Right? That's something we haven't really seen before. And that trick is a good trick. Again, it's a trick that can be, like I said, can be used in other settings. And that's something to remember, that this is how they're trying to go about their problem, to separate out the two concerns and put this kind of shield in the middle, which is a new representation. Okay? It's like, everyone goes into a room and they come out with a different colored bag over their face, right? So you can't see their face, all you can see is the color of their bag. And you have to make your decisions based on the color of their bag. So a version of this, actually, a very extreme version of this, comes up in auditioning for being employed by an orchestra. And I don't know how many of you know about this, but for a long time, symphony orchestras were very heavily male-dominated, right? And back in the, till the early 70s. And there were lots of reasons given for this. Among them, they play differently, the sound is different, this is the sound we need, all the usual silly reasons people give for these kinds of things. And then someone said, okay, let's try an experiment where we will have performers perform for selection. So you have to go to an audition, right? So you got to perform a piece for the orchestra behind a curtain. So you've all seen The Voice, right? Isn't that how The Voice works? The judges don't see the person singing, and at the end they turn around. Was that The Voice? That's The Voice, right? So then at the end they turn around, they see the person. So same thing, but without the flashy lights. The orchestra members sit and listen to someone playing behind a curtain, and they make the decision based on that. And the minute they did that, suddenly, miraculously, the gender ratio started improving in orchestras across the world. And this is one of the standard methods they use now to do auditioning. It's called blind auditioning, right? And the numbers went up so dramatically that people wrote papers on how stark the change was. Somehow the musicality was no longer an issue once they were behind the curtain. So this idea here, right, of creating this curtain, right, with these K representatives to hide other information is in some sense a much more elaborate generalization of that very simple trick of blind audition. Okay. All right. This paper and another paper like it introduced this notion of fairness that I talked about, was it 2 days ago now, called equalizing odds. So if you remember that we had talked about this idea that we keep talking about statistical parity as, okay, the classifier value is equal to 1, given the group value is equal to 0, should be roughly the same as the probability of selection given that the group value is equal to 1. And we said that one of the potential issues with this was that it was fixing this firm kind of equalizing argument that did not seem to reflect maybe the idea that, well, there were natural discrepancies in the population that were okay, and that what instead you wanted to do was balance out the errors that you made on different populations, not the decisions. So, if you hired a bunch of incompetent people from one group, you should have the same number of incompetent people from the other group. And the way to formalize this, what to say was that what you want is that the probability of misclassification, so your classification and the true classification, right, given one group, should be roughly the same as the probability of misclassification given the other group, right? And so this is different from the previous case because now you're actually introducing the ground truth into the equation because you're talking about errors. You're not talking about the actual decision itself, right? And so this notion is what they call disparate mistreatment. So in other words, if these two numbers are not equal, right, then this is called disparate mistreatment in order to contrast it with disparate impact. Okay? These words, they're just words they made up, but it's just a different way of thinking about it. Okay? So in other words, here's what you want, right? So and you want to do this in both cases. In the combination case, so I'll write down a bunch of things that you want. So what you want is that, well, first of all, you want this. You also want a specific case of, question? Okay. So, so another way of saying this is that you not only want these things to match, you want them to match in the case when you have true negatives and the case when you have true positives as well. So there are three different conditions you can write down here, which are all basically the same thing as saying you want the mistreatment to be more or less the same for the false positives, for the false negatives, for the true positives, for the true negatives, everything. Okay? Okay. And as always, you can think of this as some kind of optimization. So you can set up the whole problem as saying, okay, I want to minimize some function of my parameters of the classifier that I'm building, subject to constraints, fairness constraints of this kind. Right? So you can write down some cost functions. Okay, I want these fairness constraints to be satisfied. I want to find the best classifier that I can work with subject to these constraints. And you can express these constraints maybe not exactly as kind of approximate constraints as well. Right? This is a standard way to do this stuff. The problem, of course, is that these optimizations are hard to do. In general, constrained optimizations are hard to do. And so what the idea is to somehow encode these conditions as something more numerical that you can actually quantify. And this is where we're going to talk a little bit about this idea of mutual information and covariance that we talked about earlier in the morning and what the connection is. Okay? All right. So in order to do this, we will introduce the idea of a decision boundary, just like before. Well, we've seen the decision boundary before, but I want to capture this idea of a distance to the decision boundary. So I have some parameters theta. The parameters theta define a classifier. Once I have a classifier, I have a point. I can say, okay, how far is the point from the boundary? Right? We talked about margin. We've been talking about these ideas, right? So I can define some function, d theta of x, which is the decision distance. So it will be a signed distance, which means that if you're on one side, it's minus something. If you're on the other side, it's plus something, right? So it's not just a distance, it's got a sign attached to it. Signed distance to decision boundary. Okay? And once I have this, I can define this. I'm going to define an auxiliary function which tells me something about the compatibility between this classification based on this algorithm and the true answer. So in other words, g theta y comma x, okay, where y is the true label of a point, is going to be, let's see if I can get this right. Yeah, it's going to be, for example, so if they match, this number is big. If they don't match, it's 0. Okay. Okay. And here's what I want. So okay. Maybe I should use more consistently, use notation better here. Let's call this C star. All right. Here's the idea. What we will look at so remember that what we want is in general, if we have this variable, group variable G, and we have the outcome variable C, right? What we want is that the information between them is small, so that has low okay. And of course, it's hard to quantify this and sort of express this as a direct constraint, which is what we want to do. So what we're going to do is, as a proxy for mutual information, we're going to use a covariance. And what we're going to say instead is that, and people in the audience who understand this can actually help me understand this better, because I'm still feeling like I don't fully understand it, is that we will write down the covariance function, right, or the covariance of the variables between the G here. Well, that's unfortunate. Okay, well, sorry, I used the same G. I shouldn't have done that. And this variable G theta C X here. And what that means is that if you do the calculations of what this means, the covariance of two variables is the expected value of their normalized with respect to the mean product. So the covariance of X and Y so it's the covariance of two variables is the expected value of the product of the variable minus mean times the other variable minus its own mean, so normalized. Okay? So if we put that in expression in here, and you replace the expectation by actual values in the sample, what you get is roughly something like 1 over n, where n is the number of data points. So these are the, G. So these are the protected attributes, okay? So these are the attributes you're worried about, times G theta, C star X. So for each point, yeah, my notation is a little bit off, but this is the group attribute, the sensitive attribute that you're worried about. Yeah, I know, I made a mistake. I should have used something different. What would be the minimal change I could do here? Maybe let's change this. Yeah. Okay, so what's going on here? So here might be one way to think about this, right? So remember that this function is capturing in some sense some kind of, so let's say that C star is 1, okay? And let's say that you're also on the positive side. So this is some number that gets larger the further away you get from the boundary, right? And this is the sensitive attribute. If your sensitive attribute correlates well with how far you are away from the boundary, then the sensitive attribute is being useful in predicting which direction you're going to go in. That's the idea. Remember, we wanted to capture a notion of mutual information between the sensitive attribute and the outcome. But if we're now saying that for a point, its distance from the boundary is well correlated with, has good relationships with the sensitive attribute, then you're saying that there's a signal that's going from here to here. And that's what we don't want. So you want this covariance to be small. Okay? So the larger this covariance is, the more related these things are. In a perfect world, they kind of all lined up perfectly. In which case, this is a perfect predictor of this. You don't want that. What you want is that these things to be unpredictable completely. So you want the covariance to be small. So by doing this operation here, and you can choose this function h to be different functions, what they show, which is kind of clever, is that you can capture these different kinds of inequalities as proxies with this function here. By changing this ever so slightly, you can get any of these inequalities. You can capture the essence of one of these inequalities. And so when you finally write down this covariance function, you can now, as a constraint that you want to throw in, you say, instead of putting in all these inequality constraints, just say that you want this covariance. So now your new constraint going to be here is going to be subject to the covariance of g and h theta of x, absolute value is less than some threshold. In other words, it's the same idea as the regularization technique that we saw for logistic regression. The trick here is two parts. First of all, how do you encode a regularizer for this different definition of fairness? Okay? And then how do you encode it in a way that you can actually do a minimization? So in the rest of the paper, what they say is that this function is not as nice as you would like, but there are ways to simplify it, and they spend some time discussing how to optimize this function. And again, if you read the paper, they have some details about this. There's a certain kind of convex-concave optimization that you can do. It's a back and forth thing. But the main, again, idea here is that you can take this general idea of disparate mistreatment, use this intuition we have about mutual information, translate it into a covariance, which is a bit easier of a beast to work with, and plug it into your optimization. So again, you have a fairness regularized classifier, but for a different kind of fairness, with a different kind of regularization. Okay. If you look at what's going on here, this exactly encodes this. And not this one, sorry, this one. And there's a different version of this. So for example, if you do this, this one, what this one does, it says, if C star is -1, you don't care what goes on. If C star is +1, then you do care. So that takes care of the third constraint here. And so there are different ways you can play this game to actually encode it. So that it really is encoding this in a very clever way.
And why put a hard constraint to covariance versus nana rather than
That's a soft constraint, it's not a hard constraint. Oh, you're saying you want to put it up in the optimization with a Lagrange multiplier? Sure. Why not? These are just matters of taste. I don't think there's, yeah. It all depends on what how important you think certain constraints are. Right? This is, whether you put something in the optimizer or if you drop it as a constraint, that's sort of a design choice that you make when you implement your system and that you can try. Other questions? I feel like we need to increase the sugar level in the room. Speaking of which, are we ready for the break, or should we have are we going to have a break today? Normally, I wasn't sure if we're ready for a break yet, so this might be an easy time to do it. So. In the meantime. Which formula?
Like 1 by n
right? So I said Yeah, that's what I want to compute, right? And this is the covariance. Okay, so are you talking about the same question I think that you had about there's a term missing? Okay, so we are right. Let me explain this. We talked about this in the break, so I'll explain this to all. So this is the real covariance, right? Right? This is the real covariance because this is my x minus x bar. This is my y minus y bar. Right? Okay, so there are two terms here. There is this term, and then there's that term. Okay? This term is the one we end up having to compute. This term, this is a constant, it's mu, it's a mean value. So you end up with, this term basically becomes okay? But the expectation of a variable minus its mean is always 0. So this goes away. And so all we have left is, this just becomes okay? And then this we just replace by the sample covariance. You just add them all up. You just take the average of them. Does that make sense? Okay. Okay. So we're almost through to the end of this whole discussion of fairness-aware classifiers. We have one more setting to consider. Okay? And this is the setting where we were looking at online or sequential learning, the setting of bandits, right? And so since we haven't really spent much time talking about bandits, except for the first time I introduced it, maybe I thought I'll take a few minutes to remind us all of what a bandit setting looks like, what learning looks like, and then we'll talk about, and what fairness looked like in that context, and then we'll describe an algorithm for doing this. Okay? All right. So recall that in the case of sequential learning, we wanted to model the problem as this kind of bandit problem, where you have these, and again, this is called a bandit problem because these slot machines, for some reason, were called multi-arm bandits. So you have, again, a big machine, you have levers, you pull a lever and money comes out. Well, of course, that catches you to put money in first, then you pull the lever, and then sometimes money comes out. That's how the gambling works. Right? So the way we formalize this problem is that you have k levers, right? And associated with each lever is a hidden distribution with a hidden mean. And this distribution is a distribution over rewards, the amount of money it's going to give out. So the first lever might say, okay, my average reward is 500 rupees with a variance of 20. My second lever has an average reward of 100 rupees with a variance of 50, and so on, so on, so forth. Or the mean of, sorry, yeah. So I didn't talk about variance, just the mean. So put this distribution there. So you have all these different levers, right? And so, okay, what's the game? The game here is that you, as the algorithm, have to decide which lever to pull, right? So you pull a lever. And in practice, what's going to happen is that you will have some kind of distribution you're maintaining over levers, and you'll pick a random sample from that distribution to decide which one to actually pull. So that distribution is your policy, is your plan of what you want to do, right? Remember we talked about the levers as your advisors. You're deciding which advisor to ask a question to. Right? So and then you do that and you get some reward. So the game is at every step t. Before the game starts at time t, the algorithm has some kind of policy, pi t, which is a distribution over the arms. Okay? And so step 1, the algorithm samples some j, actually I think we called it it, some lever from pi, right? It pulls the lever, and A gets reward RIT, which is distributed according to DIT. And we don't know what D is, but you get some reward, right? And then the algorithm might update pi t, maybe, whatever it wants to do. This is part of what the algorithm thinks to do, and then it repeats. Right? Remember all this? So since you're pulling a lever and getting rewarded every step, you're getting something. But the question is, are you getting as much as you possibly can? Right? And so the way to talk about as much as you possibly can was to talk about, well, what is the best possible scenario? And we said that, oh, look, if you actually knew what the mu i's were, then the correct answer would be to always pick the lever with the best mu I, if you were trying to maximize your expected reward. Right? So let's say that lever J is equal to the argmax of the mu I. So this is the lever that has the best expected reward. So then the optimal, so you see what happens after t time steps. After t time steps, the best strategy is to keep pulling mu J. So then the reward you're going to get in expectation will be t times mu J. Again, an expectation. But what is your expected reward? Well, your expected reward is, well, first of all, you have to sample something from your distribution. So there's an expectation over that, right? So over IT belonging to pi t, right? And then in that case, what you're getting is the expected value of this reward. Well, the expected value of this reward is mu. So it's sum over t is equal to 1 to t mu I t, right? And so the only flexibility this is called regret, right? This is the amount you regret having left on the table because you weren't smart enough to pull this lever all the time, and you want to minimize regret. Okay? I always think of someone playing a very sad song in the background as you minimize regret. It's like you look wistfully off into the distance and you look at all your money going away. I'll stop now. So. But when you want to minimize regret, now the only knobs your algorithm has at its disposal is the pi, the strategy it picks for deciding which lever to pick. So in some sense, the process of learning is the process of figuring out a good pi. Because once you figure out a good pi, then this whole process just runs itself. But this is the only place where you get some uncertainty. And intuitively, what you want pi to do is kind of zone in on where the good stuff is. Right? So you're exploring the space of levers, pulling stuff. It's like, oh, this one is constantly getting me good stuff, and you start giving that more probability in the hope that eventually you do something. Okay? And it turns out you can show that the regret you can get from this, I didn't mention this last time, but the regret you can get from this is something like k square root of the number of arms and time, which is actually pretty good. So the total regret you pay. This is called the cumulative regret because you're basically adding up the regret for every step. I mean, this is quite nice because as a function of time, if you look at the average regret, that's actually going to 0. Right? This absolute value, of course, is increasing, but in an average sense, it's going to 0. So it's quite a good bound. Okay? Now, we talked about fairness in this context. And what we said was that the way to think about fairness here is to look at the choices the algorithm makes when it has to decide which lever to pick. And so what we said was that if you look at the algorithm's preferences, right, the algorithm is deciding which lever to pick. If you think of levers as people, the algorithm is like which person to select, right? And its preferences for which person to select are encoded in pi, right? So we can talk about if you look at all possible histories, so that you can run this with different histories, right? And so you can say, okay, for any given history, what is the probability at time t that you'll pick bar j, given the history so far? So h is the history of everything you've done so far, and as a result of a history, your algorithm has been changing pi. So in terms of that history, what is the probability that you would pick j at time t? And let's say that this is more than the probability of picking j prime at time t. And so the nice I think phrase that Professor Shaker had was, what you want is that you don't want unexplained or unjustified preferences driving your outcome. In other words, the only reason you should prefer this over that is if there's some good reason for it. And the only good reason could possibly be if right? So if it really was more rewarding to pull this lever versus that, then yeah, sure, go ahead, do it. But that should be the only reason. There shouldn't be some other secret reason why you're preferring one over the other. Okay? So this was kind of an online version of the individual fairness criterion in some sense. You can think of the generalization to this idea here. And so the goal was then to say, okay, in this setting, can I actually learn, get a good reward? In other words, do well, be accurate in the language of batch learning. Can I get a good reward while still maintaining this property? Okay? And so the question is again, how do you build a mechanism? This was just a definition of fairness. How do you build an actual algorithm that can achieve that? Okay? And that's what I want to talk about next. So this is just again a refresher from what we saw 2 days ago. But before I go on, let's make sure we are comfortable with these notions here. Are there any questions here? Yeah.
The batch classification, there was a conflict between fairness and good results.
Yeah.
Does it look like there is a conflict here?
The conflict here will not show up just yet. It will show up when we look at the performance of the algorithm. So suppose as it will turn out, so you're asking me to reveal the last page of the book here, but it'll turn out that the algorithm you get for learning or getting that has good regret will not get this good regret. It'll be worse. And so in some sense, you will have more regret if you're more fair. Which is what you'd expect, right? Again, the trade-off. This is not the counterintuitive result. This is what you'd expect, that you're paying some price for being fair. You seem shocked.
It is reasonable to pick some strategy which has more of me.
More?
More like, the policy should, the constraint here is the policy should pick some lever only if it has more.
The problem is that you have to be, in order to maintain this criterion, it'll turn out that you have to be very conservative about your strategy. And that slows you down. That's the intuition. But I'm going to go into this in more detail, and we'll see what happens. Okay? So hold that thought. Any other questions before I go on? Okay. What I'm going to do now is, as it turns out, the algorithm for solving the problem, for finding a good reward outcome while maintaining fairness, looks very much like the algorithm for getting a good reward outcome without caring about fairness at all. So the original algorithm for this problem. Okay? Which is nice because that means I can explain the simpler algorithm and then describe the more complicated algorithm, but give you some intuition as to why it has to work that way. Okay? So what I'm going to do now is actually tell you about one of the more well-known and classic algorithms for this problem without worrying about the fairness constraint. Okay? And then I will tell you how it gets modified in order to get the fairness constraint. Okay? Okay. So we talked a little bit about what might be a good strategy for doing these things, for coming up with this algorithm here. We talked a little bit about this, right? Maybe we can refresh our memory as to what we thought might be a good strategy for solving this problem. So what would you do? So you have these levers. You know they have some unknown mean. You also know that if you knew the mean, life would be good. You could figure out what to do. But you don't know the mean. But you can sample. So you can kind of sample from them. But you don't want to sample too much. Like you don't want to keep pulling a lever over and over again, which you could do to get its mean, then pull the next lever. That might be too much work. But you want to do something like that. Because again, the goal is to merely find the best one. You don't need to find the values for everyone. If something looks really terrible, you can discard it quickly. So, given those thoughts, what might be something you might try to do? Just as a thought. The question is, what strategy might we adopt to try and solve this problem, to try and balance out exploring, something very simple. So what's the initial thing that might come to mind to try?
We have to collect the data as well as we have to collect the history.
Yes, good. So say more.
Like we will collect the data set and then we have to arrange this data set.
So there's no data set, remember. There is a history of our transaction, there's no data set. Right? Because we're creating the data as we go along. Okay. So we have to pull a lever first. So we pull one. Okay? It gives us some reward. What can we say about that reward? We know that it's a sample from this distribution, and that number we got is something that is hopefully, within some range of mu, but we don't know exactly what. Suppose we only had one lever. Okay? And we wanted to figure out what its true mean value of the reward was. What could we do? We could just pull it over and over again. Right? You keep getting samples from the distribution. And so suppose you have one lever, you just pull it. So you'll get values, R1, R2, right? These are all from the same lever. And then what is our estimate of the mean? The estimate of the mean, let's say if I do this t times, is going to be, right, is our estimate of mu, right? Can we say more than this though? Can we say something like, what is the chance that this number is very far away from mu? Can we say anything about that? We don't know the variance. We don't know anything. All you can do is sampling. You can estimate sample variance. And then what do you do with the sample variance once you have that estimate?
How much it deflects from the mean so that
There's a formula, right? What is this formula called? Anyone know what this formula is called? Huh? Looking at moments, right? Exactly. So you're all getting this idea. So there's this series of inequalities. They're called tail bounds that basically tell you how much you need to sample to know that your estimate is sufficiently good, right? These are called Markov inequalities, Chebyshev inequalities, and the Chebyshev inequality, of course, uses the second moment, and there are higher moments. But the big kahuna, the big monster inequality, which is used here, is what is called a Chernoff bound, a Chernoff inequality. And it looks something like this. It has many flavors, but one flavor that we'll use, right, looks like this. So, sorry, did someone say something? Okay. So let's say that we have this variable we've been estimating R, and this is our estimate here. And let's say that, R is equal to sum of Ri divided by T. And I want to know what is the probability that that y minus mu, right, is more than some number a. 1 y, r. This is what I want to know, right? I want to know what is the likelihood that I'm very far away from the mean, right? And it turns out you can actually write down a very nice bound on this. If you have t samples, this number, so let me write a different version of this. I'll write a one-sided version of this, which looks like this. Sorry, I know you all were scribbling. I hope I didn't. So this is a one-sided version. It's saying, what is the probability that your estimate is so low that it's far away from the mean? That even if you add this number a to it, you won't get to the mean, right? So intuitively, the more samples we get, the less likely this should happen as long as, as a gets bigger, right? Or if you fix a, increase the number of samples, this probably should become less and less and less. And in fact, you can be very precise about this. You can say that this probability looks something like this. In other words, as the number of samples you take increases, the chance of you being off from the mean by more than any number gets smaller and smaller and smaller. Which is intuitively makes perfect sense, right? The more samples you get, the better you should get. Also, if you make this number bigger and bigger, this number gets smaller and smaller. So in other words, for a fixed number of samples, the chance of being far away from the mean is a lot smaller than chance of being closer to the mean. So things are good, right? Things concentrate. That's the way we expect them. This is what the central limit theorem tells us, and what all these results on probability tell us. If we take these independent trials and average them, you should get concentration to the mean, which is what this is all about. Exponential concentration to the mean. Okay? But this is very good because what it says is this. It's not just a result about the tail. It's saying if you take a certain number of samples, then you know how much the error is going to look like. In particular, let's say the number of samples you take, let's see. So let's say you take, okay, so let's sort of, how do I say this? Okay, so let's take, so let's put a threshold here for this, okay? So let's say you have t samples and set A to be something like, I don't know, square root of 1 over t, okay? If you plug this expression in there, then we're saying that the probability that r plus square root of 1 over t is less than mu is less than equal to e to the minus 2, that's it, e to the minus 2, right? So this is a small number. What's even better is that if I put something like 2 over t here, you're going to get 4. That probably gets even more. So any small constant you put here goes into the power there. So the numbers drop even more sharply. Okay? What you would like though is a bound that isn't a constant, but that gets even smaller as t increases. So that goes down with t. So typically we like to see tail bounds in these things of something like 1 over t to the something. Okay, how would you get that here? If we again plug the right expressions in, what would you want to plug in to get 1 over t to something? Well, set a to be, again square root because it's a squared, something like log t over, what did I put here? T squared? Sorry? I put t over there? Yeah, over t. Right? Yeah? Then what does this become? This becomes, this tail here becomes e to the minus 2 log t. Right?
Why don't you put 2t over there?
2 here? Here? I could, but why would I want to? Oh, you mean I can afford to do it, you're saying? Sure. Let's put it here. This goes away. So we've got a probability of deviating that actually gets even less over time. It's not a constant, which is kind of cool. Right? And again, as you can see, you can change these constants. The beautiful thing here is that if I put any constant here, it doesn't just become a constant there, it goes into the exponent. This is the beautiful thing about these kinds of bounds. For example, if I make this 2, as we saw, if I remove this 2 here by multiplying this by 2 inside the square root, this becomes t squared. So you can really play games with this. And so what this is saying is that I know exactly what my distance from the mean is going to be based on how many times I pull the lever. Okay? That's the intuition. Which means that when I'm playing this game and I'm pulling levers, after a while, I actually have a pretty good sense of what the true mean of that variable is. Which is good because now I can actually start making good decisions. Okay, so do you see what's going on here? And that essentially gives us the algorithm. This is what the algorithm is. This is called the upper confidence bound algorithm. It's a very famous UCB. It's a very famous algorithm. And here's what it looks like. So the algorithm does the following. Yes?
Population size is very large and t is going to infinity.
Yeah.
So in that case, we cannot think ever of negative probability.
Right.
Power minus infinity.
That's 0 is good, right?
No, the probability is less than equal to that 0.
Right. So the probability of a bad thing happening, so this is a bad thing because my estimate is far from what the true mean should be. So we're putting an upper bound on the probability of the bad thing happening. If it goes to 0, that means it will never happen. It's less than equal to, right? It's not. I'm not going to get a negative probability while doing that, right? I mean, this is just an upper bound. So that won't be. It's not an equality. I'm not saying this is exactly probability. I'm saying it's upper bounded by that. If this goes to 0, this basically means that this event will never happen. That's all, or at least will happen with probability 0. So, okay, all right. So what does this tell us about our algorithm? So remember this sort of a is roughly equal to square root of 2 log t or log t over t, right? Think about this for a little bit. And when I give you the algorithm now, it'll all start making sense. So the algorithm looks like this. So first we want to initialize our guesses for all the means. So in the beginning, I'm just going to play each lever once, just once. Okay? So the k levers, I pull it k times. K is a constant compared to t, I don't care. So I just pull them all. So I get some initial estimate. And then what I do is, at each time step, each time t, right? Let ni equal to the number of times I was pulled. Okay? And let mu I be the current estimate of the mean. Okay? Okay. Now, we have the current estimate of the mean for this, that's r. We know that the chance that r plus this is less than the true mean is very, very small. So why not just add that compensation factor to it and then pretend those are the real means? Right? Because we know that there's a very high chance this number is close to r. It might even be above it, which is fine. Let's just add it anyway and then see what happens. So choose the j that maximizes. So we want to pick the best arm, right? So we choose the j that maximizes mu I, which is our estimate, plus this correction factor. But now each arm was pulled a different number of times, so we have to compensate for that. So it'll be mu I plus square root of log t at time t divided by ni. So this is the trick. This is my little fudge factor to make sure that I'm using my estimate but not taking it too seriously. Okay? And then get the reward, update the means, and then do this all over again. Okay? So there are a couple of interesting things that happen here when you do this. The first interesting that happens is, notice that I have a log t in the denominator and I have an ni in the, log t in the numerator, ni in the denominator, okay? What does that mean? What that means is that, suppose at some time step, I do not pull this lever. I just don't pull it. What's going to happen to its estimate? So I have currently for every arm, right, I have some kind of estimate. Let's say, okay, this is my current value and this is maybe where the true mean is. If I don't pull an arm for many time steps, what's going to happen to the estimate? So t is going to increase, right? But ni is not going to increase. So if you don't pull it for a long time, your uncertainty about the arm will increase. The value will change. So this will get bigger. Because what it's saying is that compared to the other arms, you really haven't sampled this arm enough. What that means is that if you don't pull an arm for long enough, then its number will get big enough that there's a chance that you'll actually pull it again. So there's at least the ability for you to recover from neglecting an arm. So you pulled it once, it gave you a bad answer, and because of this number, you don't pick it for a while. But if you don't pick it for a while, eventually it'll get big enough that you might pick it again, unless other things are also getting bigger. Conversely, if you do pull a lever, what happens is this number increments and your estimate goes down, which is what you want. Because as you pull it, your expected concentration for things should increase. So the more you pull it, the more it'll concentrate, and the more it'll concentrate back to this value. So this is a very cool dynamic process where these estimates are getting bigger and going up, and eventually, well, there's no eventually, you just keep playing this forever. But the point is that what you can show now is that based on this intuition, I won't go into the proof, it's more complicated, but based on this intuition, that this estimates are going to be reasonable and your reward is going to be, your regret is going to be small. And in particular, you can show that this is the regret you get. Okay? And this is just the basic bandit problem without any kind of fairness criterion. This is the upper confidence bound algorithm. Okay? So I think there's an actual log factor here, which I should have mentioned. But log factors between friends. Okay. So this is a kind of a nice algorithm in that it's sort of, well, at least sort of conforms to our intuition about what should be happening. That you should be building these estimates for the arms, and that you can quantify how off you are from an estimate. And then once you do that, you're in good shape. So are there any questions about this before I start throwing in the fairness issues? Yes. Nope. No assumption. It has a bounded mean. That's all you assume. Okay. So now, what do we do when we are worried about fairness? The challenge now is that we're making these decisions, right? And we're choosing these estimates. It's going to be hard to infer what these probabilities are going to be based on the estimates we're getting so far. And there's no reason to believe that you actually will satisfy this criteria. And so, what this criterion is basically telling you is that if you have any reason to believe that these two could be similar, you better be careful about which one you pick. Right? That's what this is saying. Right? If they're, yeah. So you need more information than just this individual estimate of where each arm is. Right? In some sense now, before I had, before when I was just trying to run this algorithm, all I wanted for each arm was some kind of, this is my current estimate, this is how far it went, this is my current estimate, this is how far it went, this is my current estimate, this is how far it went, this is my estimate, and this is how far it went. This is all I needed to make my decision, right? So I didn't use these to make my decision, I used these, and over time these arrows shifted and shrunk and expanded and so on. But the problem now is that because if you take these two, I don't know where the true answer actually is. It could be the answer was like this. It could be the answer was like this. I'm not allowed to prefer this to that one all the time, because I don't have enough information to be sure that in fact this one was better than that. Right? Now suppose I knew that my one estimate looked like this and my other estimate looked like this. Okay? Then I'm willing to be happier about choosing this over that. They're clearly separated. But if they're not clearly separated, I don't have the luxury because of this hard fairness requirement that is preventing me from making that decision. So this presents a challenge to me as the algorithm. I have to have much stronger estimates for what's going on before I can be sure to choose one or the other. I have to still play it safe and be conservative. Okay? And so essentially what you have to do if you're the algorithm is to say, look, who was the winner from the previous round? Okay, the winner from the previous round was this one. Okay, who are the potential elements who could overlap with it in this round? Well, maybe this one is the only one, and maybe there's one more here, right? All of these are overlapping with the previous choice. All of them could be in the same range or higher. I am not allowed to have any reason to prefer one over the other. So what should I do? Well, just pick one of them at random. Pick any of these things at random. And that is the algorithm. So the algorithm says, instead of maintaining an upper confidence bound, as we've been mentioning, on the range of the mean for the arm, maintain a lower and upper bound, which by the way you can do because this Chernoff bound gives you both-sided. It doesn't just give you one, it gives you two sides. So the new algorithm, right, unlike the other one, will look something like this. So at each time t, so the state the algorithm maintains is for each arm, an interval Li and Ui. Okay, lower and upper bound on the true mean of that algorithm of the arm. Notice that before we just had an upper bound, right? We had the actual expected value and that range we had above it. Here we're going to maintain two bounds. Okay? For me?
For mu, there's a lower and upper bound.
For mu, correct, for mu. Right? And we have, of course, have our mu I estimate, right? That's also there, given to us. Okay. And we will define a notion of sort of of connections. So we'll say that arms J and J prime are connected at time t, right? If Lj t minus 1, comma Uj t minus 1 intersects Lj prime t minus 1, Uj prime t minus 1. So that if their intervals overlap, we'll say they're connected. Okay? So if you think of a graph defined on the arms as vertices, where this is the definition of an edge, you will have these connected components in this graph now. Right? So it's basically an interval graph. This set, Lj, the range from Lj minus 1 to Uj t minus 1, so the lower and upper bounds on the value of mu j at time t minus 1 intersects the interval for j prime at t minus 1. Right? So the picture here will be you have Lj and this is Lj t minus 1, Uj t minus 1, and then you have the other interval which is Lj prime t minus 1, Uj prime t minus 1. Since they're overlapping, if you think of this vertex for j, the vertex for j prime, there's an edge between them. So I get a graph on the arms and they have connected components. Okay, so keep that notion in your mind. So now what you say is, let J be the arm that won the previous round. Okay? So some arm won the previous round, right? You pulled it. And let Nj be all the neighbors of J in this graph that I just defined. So all the other arms whose intervals might overlap with J. Okay, and this includes J as well. Okay. Pick at random from Nj. Okay. So notice that unlike in the other bandit, in the other algorithm, where I just looked at each individual estimate and picked the best one, here I'm saying, well, I'm not sure who the best one is. Let me look at who was best, who just won. Look at whose intervals intersect with it, right? And then pick at random from that group because I'm not sure. And once you pick at random, update everything, update all estimates. So obviously, you'll only update estimates for the one you picked, but again, it's lower bound, upper bound, confidence intervals will all be updated, just like we saw before the Chernow bound. And you run this algorithm instead. Okay? And at least for the algorithm, that's it. The proof is a bit more complicated, but this is the basic idea. And again, you can show that this algorithm is fair. We talked about the notion of delta fair being that this is true for all possible times and for all possible J and J prime, and this will guarantee that. Now, the regret bound is slightly worse. The regret bound you get for this algorithm is something like, so remember I had the regret bound before, which was square root of kt log t. This is a bit more than that. This is square root of k cubed t log tk. There's also a delta term for the fairness, but that, again, in all of these, read the paper for the details. And the point is, this is now a little bit worse. So this goes back to the point you were asking about, should this be much worse? It's not a lot worse in terms of t, it's a little bit worse in terms of k. Because in some sense, you're dealing with, I don't know, pairs of things or more. So remember, the regret bound is the amount you pay versus what you could have if you knew the right answers. So it's not bad, it's pretty good. And so that's the idea of this method. So this, again, of course, a very, very different setting to anything we've seen so far. That's just the nature of sequential learning. It's a very different vocabulary and list of techniques. And again, if you don't take away anything else from this, knowing how the UCB works is kind of a good thing to take away from how bandits work. It's a very classic algorithm, and it's a very commonly used one. It's also nice to tell. Questions?
Would it be more useful to have something like long-term fairness rather than fairness at all times?
You might say that. But suppose you're the one who's applying for a job. Will it console you that, don't worry, we'll mess up your decision, but in the long run, we're all fine? You want the decision to be good for you now. Or as the famous economist said, in the long run, we're all dead. So no, I would argue that you want fairness at all times. You don't want eventual fairness, because what does that even mean? There is no eventual here. There's only an ongoing process. There is only the now, right? I mean, it's quite conceivable that if you relax your notion of fairness to eventual fairness, you might be able to do better. Because then you're not measuring fairness till you've figured out what's going on. Yeah? but I don't think that's a fair game to play. The other issue here with these methods also is one of consistency, right? So you have a system that's learning and making decisions. Now, if you came along tomorrow, right, and asked for a job, it might make a different decision for you than it did today. Is that fair? What do you think? What do people think? When we have an automated system that's learning, either we can say, look, we build our model, we learn it for one time and we never change it. And then we'll say, well, come on, you have to be able to update based on data. Okay, now you update based on data and now your decision will change. The same person coming in at 2 different times might look different. Which one do you think is more fair? They're both fair? So it's okay to have inconsistent decision making?
It's not really inconsistent, depending on that particular time.
That's all it changes. We are allowed to change our mind.
We're allowed to change your mind. Okay, all right.
First decision is wrong.
Sorry?
First decision is wrong.
Why is it wrong?
Because in the first decision, the one should have collected all the data in order to be.
So you're disagreeing with him. So you're actually disagreeing with him. You're saying, no, I think you should not be changing your mind.
Yes.
Ah.
So this is what happens naturally. A court decision changes new facts, but doesn't mean that the older decision is wrong. Just change.
Okay. Would you would you like to respond?
If we are changing our decision later, it means we have not taken the first decision as the correct decision.
We are not changing.
I'll just stand here. You guys talk.
Light of new evidence.
I'm sympathetic to your point of view that it's not that the old decision was wrong, it was the best at the time, but now in the light of further evidence, it's easy to say in hindsight, well, that was a horrible decision, but that's all you had. I mean, for example, there's a, I don't know, are there any good examples of the Supreme Court sort of reversing itself on decisions it's made? But has it reversed itself on any decisions in the past? It has. Is there a good example of that kind?
Because of different circumstances. Yeah.
But is there an example of this? Yeah, so is there an example?
Like we can't blame the cavemen for not using BMW or Audi. They can only afford bullets. It's like kind of that.
Wait. What just happened here?
No, I was like trying to make an analogy that within that knowledge we can make only that decision, and we are now expanding our knowledge so we can take new decisions.
Right. Yeah. So I know of many examples again.
There was a case where like Delhi High Court said section 377 that is illegal, so which of IPC which says that which basically made gay sex illegal.
Mm-hmm.
So like Delhi High Court repealed that and said like it's okay. Then like Supreme Court reversed that decision.
Right, but the question is when you reverse your own decision, right? That's the point here. I mean, it's okay to reverse. You could say, no, they're always wrong and I'm always right, but this is the case.
There are things like only a larger bench can reverse a smaller
The
bench.
decision is, there are certain decisions in which the Supreme Court, there is a very famous case about the amendment to the Constitution itself, and the 42nd Amendment, and the government said that the decision of the President cannot be challenged in any court on any grounds. And first, the court agreed, but in the light of new observations by other courts world around in similar cases which were brought to light, the Supreme Court said this is not a legal statement at all. So, thing is, in the light of not something which law has changed, but in the light of new observations,
Yes.
data which has come, it has reversed its own decisions. Likewise, the amendment of the Constitution, it said that can you modify the section which says that the Constitution can be modified. Previously, it said no, we can modify later on after people started quoting decisions all over from other courts. It said that that particular section which deals with the amendment procedure itself is not law, and it says that only the law can be changed. So, in the light of new data, it reverses its own decision. So, that particular decision was the best at that particular point.
Right.
Like suppose you are appearing for some interview and you are not selected.
Yeah.
And again after 3 days, 4 days, you again go to the interview panel, and then again you were not selected. Okay. But suppose if you are coming after suppose 6 months with more preparations, then the same panel is selected you. So,
But the more preparation is a different thing altogether. Yeah. We should keep you
something.
I know, but we should, in this argument.
Otherwise, the decision is fixed.
So,
Line of finding that other boards who were doing something have selected candidates like you, or they have they could not select candidates like you, and these people wanted candidates like you were selected. So nothing changes with you.
right,
So only that new observations change the decision.
right. I think that's the test, right? I mean, it's one thing to say you changed, and then you're not the same data point, right? You're a different data point, doesn't count.
In algorithm, we have to change our decision at each iteration.
But the data point
Sure.
is the same data, that input data, that data point, the decision has the same.
Yeah.
That means that training data or other data will come in case of online learning as the decision changes.
So I think,
The decision changes.
right, so I don't know. For the most part, the consensus appears to be that it seems reasonable to change your mind as more information comes in. That's not a bad thing, because otherwise you're just stuck with it. And so in that case, it's okay to have an online learning system that evolves and might make a different decision on the same person that it would made a month ago or something like that. But the issue of but I think this all came about because you're talking about eventual fairness. I still think that eventual fairness is not reasonable. You want fairness at all times.
The thing is, what you observed, as long as the new decision does not have any unaccountable preference.
See, I quoted you, but you weren't here, so you didn't get the chance to bask in the glory of my quoting you. So, so
The constraint of this, like, unnatural in the sense that it doesn't allow the person or whoever is using this algorithm to experiment. Like, it is constraining the experiment, not the result itself.
why is it okay to experiment on people's decisions? Why is it okay to experiment on people's lives?
Like, the result, if some experiment is allowed or not, should depend on the actual result.
But that's the result, right? The result.
I mean the impact on the people, like not on the way of experimenting itself. Like, for example, like, so if it is used in medicine, so there are specific norms and like you have to take the consent of the people and they know that they are being experimented. And like say you are having an online, like a store which shows items.
Yeah.
People. So
Yeah.
in that case, it's okay.
Let's see it this way. In 1960s, toys came and they were one drug, and everybody was prescribing on it.
Yep.
And then then came 80s and people found that it was actually harmful.
Yep.
So you would say that doctors prescribing drugs in the 60s were wrong?
Well, they were wrong, but not responsible. I mean, I would still say they were wrong, but they couldn't have known. They couldn't have known.
The decision at that time was fair.
Yeah, they couldn't have known any better. Yes, right.
But then tomorrow, knowing that attending this particular class is going to decrease your body of knowledge, doesn't mean that he becomes.
Hey. Don't listen to him. Okay. But here's an interesting point, and again, I'm diverging away from the topic, but I think this is an interesting point. We just said, as long as it's fair as long as you did the best job with the information you had at the time. Okay, now suppose someone is upset with the decision made by an algorithm. What does at the time mean? When you use data mining to build a decision-making tool, what does at the time mean? Especially if you have a system that's evolving.
So suppose there is an interview, the minimum qualification is something, and the person is not getting it. So he will be feeling bad about the decision that he is not.
But that is different.
Yes. That's not what I'm talking about. I'm saying when you say, if you want to you want to appeal a decision and say, this was an unfair decision or it was not the best decision at the time, what is at the time? So, to the extent that you are aware of how machine learning is used, do we ever checkpoint our decisions? Do we checkpoint our models? Do we actually have a sort of, okay, every time a decision gets made, we freeze the model in place, especially for a model that's evolving. We sort of take a snapshot of what parameters the model had and lock that in place with the decision and then keep a list. Do we ever do that? I don't think we do. All of this discussion suggests to me that this should be something you should do. So that you can actually, if you need to justify the decision, you have the model that can justify the decision. Or the history of the data, or the whole transcript, or whatever it was used to build that thing. Especially in a situation like this, where your history is ongoing. It's something to think about the mechanics of doing. And there's nothing to do with fairness. It's just about accountability and decision making, right? If you want to be accountable and if you want to be responsible, what should you be doing, right? And that's something that's worth thinking about, even if you don't care about any of these things.
No, but then if you look at your own decisions that you're making here, and they are data driven. As you have more data, you are making better and better and fairer decisions.
I'm making decisions, yes, but hopefully they're better. Yeah.
And the data and the decisions that you're taking, intelligent decisions that you're taking,
Yeah.
which lever to pull and which not
Yeah.
to pull, is dependent on your current state of your.
Yes, the pie, the policy I'm making. Yes, correct.
So that's the idea, that your decision has to be connected with the amount of data you're using to make that decision.
And in some sense, this goes back to this point here, right? Why do we have this at the moment criteria? Because you're saying, do the best you can to be fair with what you know right now. See, notice that this is the history right there.
But the term, the mu j greater than mu j,
Yeah.
this is not like the best we know.
No, this is what we know. This is the ground truth that we don't know, but that is the oracle, right? Again, unaccounted for preferences, right? But that's why this captures a history then. It's saying, based on what you know till now, do the right thing. Okay, we can.
Also includes like finding out more information. So
What I suggest is this is the kind of discussion you need over coffee or stronger liquid products, but we should have that thing. But what I do want to do now is say, okay, this basically marks the end of the whole arc of today's discussion. Hopefully, this rather sort of dizzying or confusing array of different techniques, you got a flavor of the different ways in which we try to combine ideas about fairness and ideas about how to build good classifiers in different settings. Okay, and that I'm done for now. So I think maybe you can talk about sort of a plan for what we want to do. Yeah, so let's talk about a plan for what we want to do. So the plan that we discussed would be, so as far as scheduling goes, so tomorrow we have a morning session, and then I will not be here for the afternoon and for the next day. I'm actually going off to IIT Kanpur, and I'll be back after that. So what we'd like you to do is so today, what's the day today? I'm so out of it. So today's Wednesday, right? So Friday morning, where your assignment for when you come to class will be to do a presentation on one of the papers that we've seen so far. So not, if you're more ambitious, you can pick one that we haven't done yet, but it might be easier to pick one that we've seen so far. And the way you're going to do it is to break up into groups of 2 or 3, maybe 3 or 4, so depending on the divisibility, and choose a paper. And I think maybe the thing to do is, I don't know, by tonight would be a good time to email Abhishek with the proposed paper that you're going to present. Would that be reasonable? So then do we?
We have time, can you make it right now? So you could present. Other people may join you.
We could do that.
So that will be better, because then the groups, because some people are local, some people are staying in guest house, some people are staying.
So if once they disperse, it'll be harder, you're saying. Okay, so shall we just take 10 minutes?
Yes.
10 minutes, self-organize, make groups. 3 or maybe 4, but no more. 2 is also okay. Go.
Okay, how much?
Some 9 groups.
9 or 10. Some of them are not present. Then we might not know.
Hey, we join them.
Okay.
Well, let's join them. Because we have said.
So what are the durations of the presentation? That will change.
Because we have 3 hours. So I think most of the answers
So
will
you mean it's more like 150 minutes to do a break. 165 minutes. So realistically, we have about 8 groups.
6 minutes. Half an hour each.
Yeah, we're pushing it. 6 groups, 25 minutes each, or what we want.
Ah.
Okay, so we need 6 groups. Welcome.
Yeah. That's okay. Okay. So, 25 minutes presentation. Okay. Like I said, it's probably best to choose one of the papers that you will go back to syllabus, see all the papers we've been covering. So choose one paper.
Make your own PPTs, don't download the PPTs.
No, I'm just telling them the PPTs are available. Yeah. Okay. And what I think would be useful to do, right? So of course I've covered some of the material in these papers in class, right? And so hopefully that will help you read the paper. But the paper has lots more details. Every time I keep saying, oh, look at the paper for details, what I mean is there's much more stuff in the paper than what I present. So I think one thing that you should definitely try to do with the paper you choose is to go into the details a little bit. Understand some of the things that maybe I didn't mention, maybe things I didn't say right or didn't clarify properly, things that are extra stuff in the paper that I didn't really cover because I'm trying to cover one idea. Pull that out, right? And talk about that a little bit as well as giving the overall picture of what the paper is about. So of course, like any good presentation, we should have, what are the things we should have? We should have an introduction, brief introduction, right? So set the context for why the paper is written. So whenever I tell students how to present papers, right? And so one of the things I always say is every paper has to have a reason for existing. It was written for a reason. What is that reason? It's not enough to say I did something. No one cares. What did you do that was actually interesting? What did you do that was different? What did you do that pushed the state of the art in some way that was not there before? This requires an understanding of the context in which the paper came from. No paper is in a vacuum. Every paper builds on things that came before it and is at a point to things that will come in later. We're not going to worry about the later part, but definitely a paper builds on what came before and does something new and original over and above what happened. What is that new and original? What's that delta? What problem are they solving? You'll be surprised how many presentations said, this paper, here's the algorithm for this paper. And then 10 minutes in, I'm like, well, what is the problem they're trying to solve? And the speaker has forgotten to mention that. So state the problem. What is the problem you're solving? What is so interesting about the problem? Is it a boring problem? Is it a nice problem? It's an interesting problem. And then what do they do? What is their key idea? The key idea is not 3 sections of algorithms. The key idea might be something buried inside. And again, I've talked about some of the key ideas. Your job is to go a bit more into detail with those things. Okay? So try to do all of it. So introduction, context, main ideas. You don't have to be horribly detailed. Okay? Unless you think that's what you want to emphasize. You have to make a choice. What is it about the paper you think is worth telling this audience about that they have in front of them you might find interesting? And then tell them. You don't have to be comprehensive, you don't have to be exhaustive. You have to be interesting. Okay? So that's what your presentation should contain. Do we want people to sort of, everyone to present a little bit? Because if there are big groups in 25 minutes, maybe you can have everyone take it.
Not everyone, maybe not everyone. Anybody can present.
Yeah.
But
they must present. So that when he asks you his scary questions, you can actually answer them. Okay? Alright. Is there anything else you think would be worth adding to this? Any questions? It's good? Okay.
if they want some kind of preparation, then you'll have to find out which kind of
Yeah. Sorry?
An important result. Means like main idea, then maybe some result, maybe some.
Yeah, main result. So the key result, right? And again, you choose. Part of the art of presentation is your decision as to what you will present and what you will not present. That gives a picture of the paper, right? So you have to decide. It's not just everything. You're deciding what you think is important. Students, any questions about this? About the plan? So this is going to be easy.
And if you choose to prepare your